So for instance, people have been interested in the so-called serial interval, roughly the time between successive cases as a disease is transmitted, and Bayesian inference has been used for that. That's one of the papers here. People have been interested in understanding the effects of interventions like lockdowns or schools closing, and that's two of the papers here, and Bayesian inference has been used in both of those. Of course, again, there's many, many more. Now, some of the scientific discoveries of the recent past perhaps are a little bit more fun to talk about. So one of these is the exoplanets discovery of these, exoplanets in the TRAPPIST-1 system. Really exciting discovery. And in this case, Bayesian inference was used to get point estimates and uncertainties of candidate observations to determine which ones could be safely categorized as exoplanets. And I should say, in the previous example too with coronavirus, people are interested in, again, not just estimates of things like the serial interval or the effect of lockdowns, but uncertainties as well to know, are we really sure that these things are working, or that we know what we think we know. Another big recent discovery was the discovery of gravitational waves. So here Bayesian inference was used to figure out things like point estimates and uncertainties in things like the mass and spin of the black hole that was emanating these gravitational waves. Tragically, in 2009, an Air France plane crashed in the Atlantic Ocean, and for many years, people were trying to find the wreckage. It's really important to find sort of the black box and understand what happened in these cases so it never happens again. And there was just no luck. And then, a couple years in, people brought in somebody practicing a form of Bayesian inference, and they were able to find it in a couple of weeks. Now, of course, they had the information from these previous searches, but that's still pretty exciting. When you are interested in something like understanding, how are you going to route maybe an ambulance to help somebody who has some really serious health problems and they need hospital attention immediately, you're really interested in not necessarily just point estimates, but uncertainties. Let's say you're deciding between route A and route B, and route A takes on average, let's say 9 minutes, and route B takes on average 10 minutes. You might think, route A sounds better. Let's get to the hospital quick. But maybe you need a life-saving procedure in 13 minutes, and suddenly 9 plus or minus 5 might look worse than 10 plus or minus 1, just because you're certain to arrive at the hospital in time. Now, also in the social sciences, economists like Rachel Meager have used Bayesian inference to understand things like microcredit, these small loans to individuals in impoverished areas. And we really want to know, are they effective? Are these actually helping people get out of poverty? There's also things like Hamza Balakrishnan at MIT has studied planes and understanding their fuel usage based on their routes. And so this can be really useful for improving fuel usage, for understanding what's happening, maybe even regulatory purposes. Fishery management is another case where we really care about uncertainty and risk, because there's this risk of potentially losing all of the fish, a population of fish. And so this can be really useful in this case. Okay, so here's just a ton of examples. And again, this is just a few, there are many more. But I think one thing that we can see from this set of examples is, what are we trying to get out of Bayesian inference? And I think what we're really seeing in these examples, at least, is that we want point estimates of some unknown quantity. So we want an estimate of that quantity. But we also want to know not just what do we know, but how well do we know it? So this is super important for science, but also more generally decision-making, in engineering, and so on. Okay, and then of course there are other reasons that people use Bayesian inference as well. It can be relatively interpretable in the sense that you can specify exactly the parameters that you're interested in, and then try to learn the values of those parameters. It's modular, so if you have an idea of sort of how physical processes work, or how various components in a process fit together, you can encode that, and that can be useful from a practical standpoint as well. And sort of more generally, you can encode expert information in various ways. So certainly in all of these cases, there are a number of experts that already exist. They have a lot of expertise that we would like to encode in the problem. And that's certainly something that you see in all of these applications. Okay, So not only is Bayesian inference very widespread, but there are excellent tools for it these days. This is a super non-exhaustive list of the amazing probabilistic programming languages that are out there. Just a couple of examples are TensorFlow has a really nice probabilistic programming language. Stan is extremely widely used. I think, you know, it's downloaded something like tens of thousands of times every month. And actually, I think that's pretty old information at this point. I think it's, you know, even more widely used than that statistic might suggest. Okay, so that all sounds really great. Bayesian inference is used all the time, and we have this probabilistic programming languages that do it really well. And so what's the problem? Is everything solved and we don't need to keep talking? Well, no, there are a lot of challenges to Bayesian inference, a lot of practical challenges in person. And so let's say, you know, what are three sort of goals that we really want for Bayesian inference? Well, one, of course, is compute speed. So if I'm doing a study on coronavirus, and you know, this data comes out in March and I really want to get my study out to save lives immediately, I don't want to have to wait a month for my Bayesian inference to run in order to even be able to see the result. And then personally, I find that anytime I do any form of machine learning, I run my code, and then after I run my code, I realize that there were bugs in my code. And so then I have to run it again and so on. And so it's not like one run is your real cost. You know, it's really like you have to run that multiple times. And so anything that costs a really large compute time is going to be prohibitive. And we can just really see in some of these examples that that's going to be, you know, a real problem for those applications. Okay, now something that I think is really important to keep in mind is that compute time isn't the only time that we care about. User time is a huge part of timing. So, you know, let's say that, you know, you're a biologist, and again, you're interested in some study of coronavirus, and, you know, your compute time is super fast, but it's going to take you 6 months to derive equations to do anything. Well, again, that's not good enough. We want somebody to be able to do their awesome science that saves lives, you know, or gets at some really cool scientific discovery, and we don't want it to take 6 months or a year, especially in these time-sensitive situations. And so their user time really matters as well. It's something that we have to keep in mind. And then finally, of course, we care about reliable inference. You know, I can easily come up with an algorithm that is fast in compute time and fast in user time. And here is my algorithm. It returns the number 6. It's super fast. It's literally constant time. You can't get much faster than an algorithm that just returns the number 6. It's fast in user time. There's no tuning. There's nothing you have to do. But I think this example illustrates why you have to be skeptical of something that just says it's fast, because it's easy to just be fast. It's hard to be fast and accurate. And so that's why we really have to, whenever we talk about speed, we just have to simultaneously talk about quality. What is the quality of the inference? And so this is the real challenge, that there are a lot of methods that are out there right now that are really high quality, but are extremely slow. And likewise, there are methods that are very fast, but may not be so high quality. And so how do we get Bayesian inference that is fast and high quality and supports all of this awesome science and engineering that people are doing? That's the real challenge that we're facing. And I think it's just really an open challenge. So today we're going to talk about variational Bayes as one of the methods that people have suggested for addressing this challenge. And before I go on and talk sort of more specifically about variational Bayes as a potential solution, I do want to just mention there's this sort of point that sometimes comes up, and people think that, you know, well, do we even need Bayesian inference for our modern very large data sets, because doesn't uncertainty just disappear? And I want to push back on that a little bit, because I think if you have a very large data set and all you care about is one parameter in that data set, like an average of the data set, then yes, absolutely, it disappears. But I think that's not the way that we interact with our modern very large data sets. You know, if you think about a giant data set from Amazon or Walmart, you know, it's not just that you have these purchases that people are making for products that everybody is purchasing, but you have this extremely long tail of products that not everybody is purchasing. Same thing with, you think about something like, you know, Uber data set or traffic data set. Yeah, there are some roads that everybody travels on, but there's still uncertainty from different times of day, and there's just being noisiness there. But also there are roads that are much less traveled on, and we still want to be able to say something about those. And so I think in general, when we have very large data sets, it's not just that we're asking a single question and we get more and more data about that question, it's that we're asking more questions. And that's what, you know, retains the uncertainty that we have. Okay, so that's a Bayesian inference setup. This is why we care about Bayesian inference. And so now we want to think about, what are ways that we could address this challenge that we talked about, getting speed and accuracy at the same time. And certainly variational Bayes is one of the proposals out there for dealing with this. So as we just said, modern problems have both not just large data, but also large dimensions. And this is really where variational Bayes excels, at least in certain ways. And I think just the thing that is really the selling point for variational Bayes is that it can be extremely fast. And so for that reason, we see that it's used on essentially modern very large data sets. So giant text corpuses have just been a huge point of interest for variational Bayes. Increasingly, we have tons of data on networks, like social networks get very, very large. Neuroscience data can get very large, especially very high dimensional. And then various forms of biology and genomics data also get very large and very challenging. So these are all cases where people are using variational Bayes. They're using it because they have such large challenging data sets. And so we'd like to understand what's going on with variational Bayes. I mean, I think a very general lesson in machine learning is that there is no perfect machine learning algorithm, but these are useful tools in a toolbox. And so for every algorithm that you encounter, you should ask yourself, what are the benefits of it, and what are the things that you should be aware of, that might be some failure modes. And everything has them, and so you want to figure out what those are. Okay, so today we'll start by going into a little bit more depth in what exactly are we doing in Bayesian inference, and what does it mean to be doing approximate Bayesian inference. Then we'll start defining what exactly is variational Bayes, and it turns out there's a particular form of variational Bayes that's extremely widely used. If you just read a paper about variational Bayes or that's using variational Bayes, there's a really good chance that it's what's known as mean field variational Bayes. So we'll say what that is as well. And then we'll talk about why should you use variational Bayes, like what is helpful about it, what are its benefits, how does it work in practice? And then we'll talk about some potentially pitfalls. As I just mentioned, I think every method has some pitfalls. Just because you don't know what they are doesn't mean they don't exist. And so we should ask ourselves here, as in every other method, when can we trust this? And are there any downfalls? And then we'll talk about where do we go from here. Now, I want to mention, we're not going to do all of this in today's session. We're just going to get started in today's session. But by the end, we'll have addressed all of these points. Okay, so let's start with this review. Just reviewing what is Bayes and what is approximate Bayes. Okay, so Bayesian inference, we're interested in some parameters. These are the unknowns, the things that we're interested in learning about, like for instance, the serial interval of coronavirus or the mass and spin of the black hole that's emanating gravitational waves. It's something we don't know, but we want to know about. We start off with a prior in Bayesian inference. This is sort of expressing what do we know going into the problem before we've seen any data. Then we will collect some data. Now here, I'm just having sort of a cartoon of Bayesian inference. And it's worth recognizing what's a cartoon about this. We as humans can only see in 2 dimensions. And so here I'm plotting essentially a one-dimensional parameter. But of course, in real life, we have these very high-dimensional challenging parameters. And so, take this cartoon with a grain of salt, but I think it gives at least a little intuition. Okay, so we collect our data. Let's call our data Y. We'll say that our data is Y1 up to Y capital N. So we have capital N data points. And we're going to abbreviate that as Y1 colon N for our data set. Our likelihood will be the probability of the data given the parameter. So this sort of describes how the data might be generated if we knew the parameter value. And then finally, the idea of Bayesian inference is to calculate the posterior. So if the prior is what we knew before we saw any data, the posterior is what we know after having seen the data. And the cartoon here concludes sort of saying, okay, we applied this fact of probability, Bayes' theorem, that relates our data and our parameter, and we learn something about the parameter. And the way that we can express that is that our uncertainty has decreased, sort of the width of this distribution roughly has decreased. And now we have a better idea of sort of what is the parameter value. Okay, so how do we use Bayes in practice? Well, there's essentially 3 steps. So the first step is you have to choose a prior and you have to choose a likelihood. That's essentially those 2 things together form a model, or what might be called a generative model. Now, this could be an entire lecture series on its own. And so I want to say this is like a really challenging and important set of questions, and it's just not what we're going to get into today. I'm going to assume that we have a model, that some scientists have consulted with us and come up with a super cool model. And we're going to focus on the next steps in Bayesian inference, which are we have to now, once we have our prior and our likelihood, we can compute the posterior. All you need is the prior, likelihood, and data to do that, because it's just, again, Bayes' theorem. And then we're going to report a summary. So the reality is, you know, whenever you're using Bayesian inference, you pretty much never report the entire posterior, especially if it's in high dimensions. You just can't visualize that or think about that. And so what you'll typically see in a paper is that somebody reports some notion of a point estimate and an uncertainty. And an example of that would be the mean of the posterior distribution, perhaps in each dimension of the parameter, and some sort of variance or covariance. Okay, so as I said, we're going to focus today on steps 2 and 3, which is not to say that step 1 isn't challenging, it's just a different kind of step. But steps 2 and 3 are challenging from a computational perspective. So let's talk about why that's the case. Why are steps 2 and 3 hard? Well, there's typically no closed form for the posterior. Yes, this is just a simple fact of probability. Once I have the prior and the likelihood, the posterior is defined, but can I actually get it? Can I actually use it? Can I report a mean and covariance? In general, there's just not going to be a super simple equation for that. So I have to approximate it somehow, or, you know, do something to get at that. But I can't just solve for it either. So there's a high dimensional integral that's going on here. And I need to think about, well, what can I do to get at that integral? And so let's just talk really briefly about why there is a high dimensional integral. So in particular, well, one, if I'm trying to do this integration, if I'm trying to figure out, oh, I think that my other, the second me on this chat may have been kicked out. I don't know if that's possible to get back in. So continuing here for the moment. So we have this this integral, and so part of the reason that might arise is because we have we need to do a mean, we need to do a variance, and so those are going to be things that involve an integral. But also, even if we just look at this equation to begin with, we have also, I think somebody may have drawn on this. I don't know if that's possible to get rid of. But if we're just solving this equation too, we can look at what is the normalizing constant. That's just the probability of the y here. And how do we get the probability of the y? Again, because all we have access to here is the prior and the likelihood. And so from that perspective, we need to do is we need to derive it from the prior and the likelihood, and that's just going to be the integral over theta. So this is the joint. We can get that from the conditional and the marginal, and we can get that by doing this theta thing. Again, I don't know if there's any admins in the room, but if it's possible to remove that drawing, that would be super. Great. Okay, so we have this high dimensional integral, and the question is, how do we solve it? So now we have to think about how to do that. Okay, so there is a gold standard for this that's so-called Markov chain Monte Carlo. It's been used for decades. I mean, it really made Bayesian inference something that we could actually use in practice, and that's been fantastic. And so what's great about it is that it's accurate if you run it for long enough, but you can sort of immediately see the problem that long enough might be really difficult. And so, this could be too slow to really run in practice. And so this is sort of the big reason that people are looking for some alternative. Thanks for getting that. This is the big reason that people are looking for some alternative. They want something that that they can run in the time that they have. Okay, so now if you think about modern machine learning, like what are people doing in modern machine learning? What are sort of the types of approaches they're taking? Well, so one of the sort of like hot things in machine learning right now is optimization. There's this feeling that optimization is really fast, that it's something that we can use to speed things up. And so one idea here is to say let's not use Markov chain Monte Carlo at all to approximate our posterior. Let's try using something else, like maybe could we use optimization? So here, remember our posterior is a distribution over theta. And so could we approximate it with some other distribution over theta? Let's call it Q star. And so the basic idea here is imagine that you have tons of different distributions. This is sort of the space of distributions. And some of them are nice. what do I mean by a nice distribution? Well, the types of things we're trying to do at the end of the day are we're trying to report posterior means, we're trying to report posterior uncertainties, maybe we're trying to get some normalized posterior. And so these should be things that are easy to compute for the distribution that we have, like a Q, any Q that's in the nice distributions. And then the whole problem is that our exact posterior is not a nice distribution, or we'd be done because we could just report the means and uncertainties and we wouldn't have to deal with any of this stuff. And so the whole problem is that that isn't a nice distribution. And so what are we going to do? Well, the idea of taking an optimization approach here is to say, well, out of all the nice distributions, maybe we could optimize to find the closest of them. So in particular, let's form an optimization problem. We now have a somewhat well-defined optimization problem, which is to say, let's take all of the nice distributions, let's call that capital Q. So here, let's look at every little q distribution in capital Q and say, out of all of them, which one is sort of the least far? So here, let's say F is some notion of farness between the two distributions here. So a nice distribution and our exact posterior, and we want to minimize that. Now, there's a reason I'm not using the word distance. You might expect to say, well, we want to minimize the distance, and that's because the thing that we're going to use in a moment is not a distance. So in particular, when we use variational Bayes, typically when people are talking about variational Bayes, they're talking about F, this notion of farness, being the KL divergence. And it's not a distance because the KL divergence, or the Kullback-Leibler divergence, is not symmetric, which would be one of the things we have at the distance. So let me just change this little cartoon a little bit so this isn't symmetric. This is KL in a particular direction. And in particular, when people use variational Bayes, they use KL in a particular direction, and we'll see in a moment why that's the case. Okay, so first, I think the first question we want to ask is why? Why KL? I mean, there's so many actual distances that are out there, right? Like total variation, Wasserstein, like we are not at a dearth of distances between distributions. And so surely we could have chosen one of those. Why are we choosing KL, and why are we choosing KL in this particular direction? Okay, well, there's going to be two sort of answers to that. So here I'm just going to give the sort of high level sociological kind of answer. And then on the next page, we'll dive a little deeper into the math. So at a very high level, it seems like it works. I mean, that's the real reason that we're talking about variational Bayes today. It seems like people are using it and they're using it well. It seems to give reasonable point estimates, which is something we said we cared about. You can actually use it as part of some sort of prediction environment as well, and those predictions seem to be pretty good. And of course, it's super fast. As we said, we're really interested in something that you can run in the time you have. Way back in 2013, we showed we can make it streaming and distributed and run on millions of documents in Wikipedia in about an hour. And of course, that's only been sped up so much since then. And so this is something that can really run at modern data set sizes, in modern data set problems that have very high dimensions, like for instance, topic modeling. And so it seems like it works is really the answer of like, why are we even talking about it? But now we want to kind of dig a little bit deeper and figure out, well, why is that? Why KL, seems to be useful, seems to be widely used. Okay, so in order to answer that question, so here I just have the optimization problem that we defined on the previous page, but it's not a well-defined optimization problem yet, right? We said that we're going to minimize over the nice distributions, this notion of farness, which is KL divergence, but we need to say, what are we going to do in terms of choosing the nice distributions, and why are we choosing this farness? So we're talking a little bit more about farness. So there was a question in the chat, how do you address the distinct support issue? So with KL, you won't have KL well defined if you don't have things on the same support. Let's first actually define KL, which I haven't done yet. And then the reality is basically that, if you have something that's going to give you something like infinite KL, you're not going to choose that. Like, that's just not going to be the thing that minimizes KL. And so that's sort of essentially the question, is that, that's not going to minimize it. In practice, what happens is you just choose things to have the same support. You choose your nice distributions to have the same support as your posterior, so that you don't run into this issue. But it's certainly something to keep in mind, and actually it's something that will come up in a subtle form as we discuss later. So it's a great question. Okay, so here let's talk about the KL. So here I'm defining the KL in the direction used by a variational Bayes. So what we're seeing here is that we have the integral of our nice distribution log our nice distribution over our posterior. And for the moment, I'm just going to assume everything has densities. I mean, I think in a lot of practical problems, that's just what you're doing. And so let's not worry about, you know, measure theoretic niceties beyond that. Okay, and now I'm going to ask a question for the audience. Yes, indeed, other divergences can address this issue, but they have their own problems. So we'll talk about that later. Okay, so let's talk about just going forward with KL for the moment. Now before I take this step, let me note there's sort of a weird chicken and egg problem here. So let's look at this problem. We're saying we're going to form the Q star that minimizes the KL between our nice distributions, for which we can do nice things like calculate means and variances and so on, and our exact posterior. Okay, so isn't that a bit of a problem, right? Because we don't have access to the exact posterior. So how could we possibly find the closest thing to the exact posterior if we can't even access it? And it seems like this isn't specific to KL. This is like you put any divergence in here. You put a Wasserstein, you put a total variation, you put whatever your favorite, you know, alpha divergence in. How could you possibly find the thing that minimizes the divergence, the farness, to your exact posterior if you don't have access to your exact posterior? So keep that in the back of your mind for a moment, and let's do a little derivation, and then we'll hopefully get some thoughts. Okay, so I'm asking a real question to the audience right now. Feel free to respond in chat, or I don't know if you have the ability to respond any other way. So perhaps in chat. What did I do to go from the first line, the definition line here, to the second line? Okay, great. So Sophia said Bayes rule, and that's essentially exactly the answer. Basically, the observation here is that the conditional distribution is the joint divided by the marginal. Yeah, we got another Bayes rule. Is perfect. So Bayes rule is just a way of expressing that the joint distribution is the conditional times the marginal. And that's what we've done here. We've just rearranged this slightly and said, hey, this joint distribution P of theta and y is P of y times P of theta given y. Or alternatively, P of theta given y is the joint divided by the marginal. So perfect. That's exactly what we've done here. Great. Okay, so now what have I done to go from the left-hand side to the right-hand side? Great. There's something I'm doing with the log. I'm expanding the log. And in particular, let me just go into a little bit more detail here. Basically, remember that log of A times B is equal to log of A plus log of B. And so here, A is the blue thing, B is the yellow thing. Okay, great. Let's do one more. Can I simplify this integral in any way? So I'm just interested in the first term in this sum. Great. I think you're all exactly on the right track here. So the observation is that P of y, which is you're all making correctly, is not a function of theta. This integral is over theta. And so that log P of y can come out. And then what we're going to get is the integral over q theta d theta, which folks have recognized correctly is 1 because q theta is a distribution. And so we'll just simplify that term to log P of y. And now I'm going to make one more slight change here, which is to say the log of 1 over a is equal to negative log a. And so all I've done is switch the sign and flipped what was in the log. Okay, great. So now I've got this alternative representation of the KL divergence, and I want to point out some really interesting things that have happened here. So first, notice that this first term, as you have all pointed out, is a constant, but now I want to point out it's a constant in Q. Now, if you look at the top of the page, the thing that we're trying to do, the optimization problem that we're trying to solve, is that we're trying to minimize this thing in Q. And so if we're trying to minimize this KL in Q, and this term is a constant in Q, we can just throw this term out. It doesn't matter. It has nothing to do with the optimization problem. We're essentially just optimizing over the second term. And so because all that really matters is the second term, it gets a special name, which I'll explain in just a second. It's called the evidence lower bound, or ELBO, E-L-B-O. Now, here's the really key point that I want to point out here. We said in the beginning, we're doing this optimization problem. We're trying to find the particular distribution Q, this nice distribution, that's sort of the closest, the least far, that minimizes the farness to our exact posterior. And this is this problem that would happen with Wasserstein or total variation or alpha divergences or KL divergences or what have you, that's a chicken and egg problem. How could you possibly say what's the closest if you don't have access to the exact posterior? And here, the sort of magical thing has happened, which is now we're optimizing over just the ELBO, and the ELBO doesn't depend on this intractable normalization constant or integration over this intractable P. We only have to have access here to the likelihood and the prior, which we know we have access to, and the data, because that's the joint. The joint here, P of theta and Y, is the likelihood times the prior. And then the integral is over Q, which at least at the moment we're saying is a nice distribution. I haven't defined what that is, although people in the chat have accurately suggested where we might be going pretty soon. But at the moment, there's just some nice distribution, and we assume we can do integrals with it. So we have this right now. And this has gotten around the problem. We have gotten away from this intractable normalizing constant. And it's worth thinking, how did this happen? And if you look back over our derivation that we all did together just now, it seems like this really depends on using the KL. That you don't just have this pop out with the Wasserstein or pop out with the total variation, or even if you look at KL in the other direction, you don't just have this normalizing constant pop out. It really just popped out really conveniently because of the form of this divergence. Okay, so while we let that marinate for a second, let me just make a couple of points. So one, you can show that the KL is greater than or equal to 0. So basically, the KL behaves like a distance except for the symmetry and things like that, but it behaves like a distance in the sense that it is always greater than or equal to 0, and it equals 0 when its arguments are equal. And so this is an exercise that I think is worth doing in the privacy of your own time later. I think it's really good to reinforce these things. And if you get stuck in any way, I encourage you to check out the Bishop textbook, Chris Bishop's Pattern Recognition and Machine Learning. It's an excellent textbook, and it will help lead you through some ideas here. The question in the chat is, what about reverse KL? So reverse KL is definitely, I don't want to suggest that people don't touch Wasserstein or total variation or reverse KL or things like that. All I want to suggest is that you don't get this super nice simplification that we just saw here, right? So what was really nice about KL in this direction, I'm sorry, I always forget which one is like forward and backward. So I'm just talking about the other KL from the one we talked about here. When you use KL in the other direction, you'll notice the integral isn't over this nice Q, it's over the full posterior that you don't have access to. And so that's what's really challenging there. Okay, great. So because KL is greater than or equal to 0, which is something that you can all prove later, but hopefully you'll agree with me now is correct, you can immediately see from that last line that it must be that the log of P of Y, remember we called P of Y the evidence earlier, that's just a name for it, is greater than or equal to the ELBO. So you just get that by saying that last line is greater than or equal to 0 and then moving the ELBO over to the other side. And so now you can immediately see, where does this term, the evidence lower bound, come from? Literally, the ELBO is a lower bound for the log evidence. And so, it's just sort of explaining that terminology a little bit. And so finally, the thing that we notice is that we had this original problem at the top of the page, which was we want to minimize the KL in this particular direction for the nice distributions relative to the exact posterior. And we can express that as maximizing the ELBO. And what's nice about doing that is now we have put it into this form that doesn't depend on this intractable normalizing constant. It doesn't depend on these things that we can't compute, and that's kind of the whole problem to compute. Okay, and so let's just recap. What we've essentially established here is YKL and YKL in this direction. And again, that's not to say you couldn't use other divergences, that you couldn't use other actual distances, but this one is convenient. It's convenient because you get rid of that intractable normalizing constant. It's convenient because you don't have to do an integral over this, posterior that you don't really have access to. You get to do an integral over these nice distributions. And so this gives a sense of what that is. So there's a question in the chat, is why here the whole data set or one instance? We're imagining that it is the whole data set. So it's sort of like, I sort of went too quickly through that. When I said Y1:n before, let's imagine that we in fact are abbreviating that as Y. So it's all of the data points that we have. Another question in the chat is the other direction, EP. Roughly, there's a little bit more that goes on with expectation propagation than just minimizing the KL. There's some nuance there, but you've got the right idea. Okay, so we've established sort of YKL in this direction. And so in some sense, we've started to form our optimization problem. We want to make a well-defined optimization problem so that we can use optimization for this approximate Bayesian inference. And at this point, we've established what our notion of farness is. It's the KL in this direction. And we still need to say what it means to be nice. What is a nice distribution? Okay. So this is the setup we have so far. We need to say, what is this capital Q? What is a nice distribution? And let's again take a step back and say, well, what we really care about is being able to calculate, posterior means, posterior covariances, maybe even normalizing constants. And so when we say a nice distribution, we mean a distribution where we can calculate means and covariances and normalizing constants. Now, if you wanted to do something else, you could have a different notion of a nice distribution. That's just the one that we're talking about right here. And so let's think about it, when can you do these things? And I'd say that there are probably two types of answers to this. So one type of answer is to say, well, gosh, if I had a low dimensional distribution, I could probably calculate means and variances and so on. And so this is the idea of so-called mean field variational Bayes, is it tries to make these questions lower dimensional questions. So essentially it says the set of nice distributions are the ones that factorize into lower dimensional distributions. So across a collection of sort of subparameters, let's call them theta j, they don't have to be one-dimensional, but they are smaller, they're sort of a part of theta, we factorize. And so you're left with lower dimensional distributions, and the hope is that those are easier to deal with. Now, a point that was raised in the chat earlier is that what really makes things easier to deal with? Like if you want to do an integral, if you wanted to do, to find a mean, you wanted to find a variance. I think the reality is exponential families are just, what makes that so much easier. And so if you look at using mean field variational Bayes in a paper or something like that, it's pretty typical that people will assume that these Q sub j's, the distributions for each of the theta j's, are in the exponential family. And we'll see an example of mean field variational Bayes in just a second. So there's a question in the chat, is this somehow linked to expectation maximization? There are in fact some very interesting links to expectational maximization. There's something called variational EM. I'm just gonna leave it at that and say, if you're interested, look up variational EM. There's also a really nice paper by Turner and Sahani, 2011, that I'll mention later, is also sort of goes into this link. And I think the Bishop book probably does too. Okay, so a super important point here is that this nice distribution idea is not a modeling assumption. We have not restricted our model in any way. And this is really important because what we really want to do in Bayesian inference is we want the scientist, we want the engineer to come up with a model that represents what is actually physically going on in life, or we want the social scientist to come up with a model that represents what they really want to get out of their social science experiment. And we want them to just do that, and now we want to find the posterior or some approximation of it. Now, this is a little bit idealistic, but like that's essentially the workflow that we're aiming for here. And so we don't want to restrict the models in any way. And at this point, we haven't. We're just saying all we do is restrict the assumptions. We restrict what we can approximate the models with. Now, that doesn't mean the approximation has to be good, and that's really the question that we're going to be asking going forward is it a good approximation? But we haven't restricted the models, and we'll see an example of that, and hopefully some things to drive that home in a second. And so just to anticipate where we're going here, let me just sort of give this example of here is a case with an exact posterior that does not satisfy this mean field assumption, because we wouldn't in general want to restrict our model to satisfy it. It would be way too restrictive. But our mean field variational Bayes approximation is nonetheless a pretty good approximation. It's sort of weird. I mean, it feels like this is like a really huge approximation to be making, and yet the mean and variance of this approximation look pretty decent. Okay, so now we have an optimization problem. We can ask ourselves, how do we solve it? And this is, again, something that I'm kind of going to table. I'm going to say there are lots of really great ways to solve optimization problems. This is a whole field, you know, in modern machine learning, is how do you solve optimization problems? We're going to talk a little bit about coordinate descent, that you could go through each of the cues and solve them. And we just know in modern optimization that that's not really the best way to go about doing things. So this will be more illustrative than me telling you that you should definitely do coordinate descent. Like you should really use whatever is a good optimization algorithm. But this is one thing we'll use for illustration. Okay, so before I go on, I just want to recap where we are at this point. So we have said we want to do approximate Bayesian inference. We have this posterior, we want to approximate it, and we're asking, how are we going to do that? And so we started by saying, hey, we're going to make a choice. We're going to use some Q star to approximate our posterior. Now, technically speaking, like going in, we don't necessarily have to do this. If all we want in the end is an approximation to the mean and variance, or the means and variances of this approximate of our posterior, maybe we don't have to go through an intermediary Q star. But this is a choice that we're going to make here. Now I'm going to go and sort of make a Venn diagram of approximate Bayesian inference. Within this, we're going to make a further choice. We're going to choose to optimize. Now, we don't have to do this. There are other ways to use a Q star to approximate our exact posterior. We could use a Laplace approximation. We could use Markov chain Monte Carlo. And that's not the direction that we're pursuing right now. We're pursuing an optimization direction. And in particular, we're pursuing this particular optimization direction. We're saying, let's minimize over the nice distributions some notion of farness. And then we made another choice. We made a choice, which is, what is the notion of farness that we could use here? Again, that's not the only possible choice. We could use total variation. We could use Wasserstein. We could use alpha divergences. There are so many other things that I'm not even mentioning right now. There are lots of choices, but this is a choice that we're using. Yes, so there's a point in the chat that this assumes the model is differentiable, and indeed, a lot of modern methods for approximate Bayesian inference assume at least some form of differentiability. You'll see that in MCMC as well with things like STAN. And it's an interesting thing to ask sort of how does this limit you and how doesn't it? But we are going to be assuming, again, things like densities. You have to be a little bit careful about what's differentiable and what's not, because we are allowing certain types of, things like discrete variables. But there is a certain notion of differentiability that's assumed in a lot of these things. Okay, so now beyond variational Bayes, we're going to make this further choice of what's a nice distribution. This isn't the only choice of nice distribution that you could have, but certainly it's a very widely used choice. If anything, I think that typically when you read a paper, they're going to be using mean field variational Bayes if they're using variational Bayes. And then finally, we can ask what types of ways we could optimize this. And there are many choices. There's coordinate descent. That's, again, usually sort of mostly used for illustration. There's things like stochastic variational inference that make this very, very fast to use on large data sets. There's things like automatic differentiation variational inference, and certainly this assumes certain forms of differentiability in order to use automatic differentiation. And this is very black box, and it makes things sort of easy to use in practice. Okay, so what I want to emphasize here is that we've made a number of choices, and these aren't the only choices we had to have made, but they're particularly popular choices, and so we want to understand how do each of these choices affect our approximate Bayesian inference. Are they good choices? Should we have made different choices? You know, what are they doing? And it's worth separating out each one too, so we know if we want to change something where that's going to be impactful. Okay, I'm going to make a quick observation, and that is what is variational Bayes. And I think the reality is that you may find that this varies a little bit from paper to paper. So the words variational Bayes essentially in some sense come from sort of calculus of variations. So, you know, sort of we have this optimization problem of functions that we're optimizing over functions, and so that's where calculus of variations comes in. You will find in papers that sometimes when people are talking about variational Bayes, they're talking about it at this level. Sometimes they use the term variational Bayes to refer to any optimization problem of this form. And sometimes they use the term variational Bayes to refer to mean field variational Bayes. So in all of these cases, the reality is you always have to check what is the paper actually doing. When they say they're doing variational Bayes, hopefully they spell it out somewhere. They say what exactly is their optimization problem, and then you know which one of these we're doing. Okay, so this is the setup. This is what we're doing today and in the following steps in terms of not just approximate Bayesian inference. This is sort of the realm of approximate Bayesian inference, but variational Bayes in particular within it, and mean field. And so I think that we're just about out of time. And so I will leave for our next meeting talking about why use variational Bayes. So I think very reasonably at this point you could say, well, why would I expect minimizing the KL to be useful at all? Why would I expect this mean field assumption, which seems really, really stringent, to be useful at all? And so we're going to walk through some examples of using this in practice next time, and basically see that it's, you know, perhaps surprisingly can work really well. But then again, beyond that, we're going to talk about, you know, are there pitfalls? Are there places where it doesn't work? And I think the reality should not be surprising to anybody who's done anything algorithmic whatsoever, that of course there will be pitfalls, and we just need to know what they are. So I think that that we are out of time for today, is my understanding. So I'll leave it there. Again, I just want to mention I'll have these slides up on my website. I'll also share them with the organizers here. And I encourage you, if you have some time before tomorrow, to consider running through some of those exercises, because I think that can really help solidify some of these ideas and get us ready to discuss sort of using this in practice. So the question was, where will the slides be shared? And so I shared a link at the beginning, but I should have shared it again here. So if you go to tamarabroderick.com, there'll be a tutorials page there, and I will put them there. And I'll also share them with the organizers, so they may well be shared on the summer school page as well. And I just want to do a quick recap before we dive into where we left off. And so before I go forward, it's my understanding is that you all have access to the slides from day one now. If you haven't already seen those, they're also at the link below, but I think that they have been distributed to all the participants. So let's just, you know, talk about where we were yesterday. So one of the big things that we spent some time on is saying, you know, Bayesian inference is used in some extremely important applications in science and medicine and engineering and the social sciences, you know, really up to like the present moment. And one of the situations that people find themselves in, you know, these scientists and engineers and social scientists, et cetera, is that they want to do Bayesian inference. They want to do it quickly. They want to do it quickly in compute time. They want to do it quickly in user time, and they want to do it quickly, and they want to do it accurately. They want to get accurate results when they're doing that. So we're essentially sort of exploring variational Bayes as a potential way to do this, to do approximate Bayesian inference, which we spent some time on yesterday. And so the one thing that I want to just go over from the slides yesterday, which hopefully you are sort of familiar with and remember, but let's jog our memories a little bit, is the choices that we had made. So we went in saying we want to do this approximate Bayesian inference. We have to approximate things because we have these sort of large high dimensional models, and you know, we can't just solve them in closed form. And so in particular, we want to get this posterior. And we're thinking of it here as a function of theta, the unknown parameter, and we've been given some data y, and remember y represents sort of all of our data, everything that we've seen. And we're going to approximate that posterior with some distribution. We call it Q star. That's just whatever we're approximating it with. And that was sort of the first choice that we made. That's a choice to approximate the posterior that way. And then we said, well, the particular form of approximation that we're going to explore today is optimization. We're going to say that Q star is the closest of a set of nice distributions. That's capital Q. So that should be distributions where we can get the things that we want out. So let's say, you know, means or variances for our point estimates and uncertainties. And F is some notion of farness. And we're explicitly not using the word distance because the types of things that we're going to be using aren't always distances. But some notion of farness between our approximation Q and our exact posterior P. And this is a choice. You could use Markov chain Monte Carlo, and that would not be an optimization problem. And then we made a further choice. We said, well, let's use a particular notion of farness to help make this a well-defined optimization problem. Let's use the KL divergence, the Kullback-Leibler divergence, in a particular direction, this direction in particular. And we spent some time justifying that, saying that it was a convenient choice. And now we want to ask, does that convenient choice do the things that we want it to do? Of course, you could make other choices here. A number of people brought up other choices in the chat that you could make. And I think that's a really interesting direction and one we'll spend a little time talking about. But something that we saw was that KL, and in particular KL in this direction, is pretty convenient because it gets rid of that normalizing constant, which sort of makes this otherwise a chicken and egg problem and a difficult optimization problem to solve. Okay, so then we said, what's a nice distribution? Well, there are lots of things that you could say are nice distributions. It just has to be some distribution where you can get out what you want. And here we're saying we want point estimates and uncertainties. This might take the form of means and variances. Certainly that's our focus today, but that doesn't have to be your focus in general, but it's certainly a common focus. And in that case, we might use so-called mean field variational base. So here we assume that the distributions that we're using as our nice distributions, factorized, so our approximating distributions. We're not making assumptions on the model, on the prior and likelihood, just on the approximation. And we pretty much always in practice assume that actually Q is in the exponential family. If you ever find something where somebody says, oh, we assumed everything really general and we're just assuming this, you know, factorization assumption, I think you'll probably find at the end of your derivations that in fact, everything worked out to be in the exponential family. Okay, so then finally, we have to solve this optimization problem somehow, and there are many ways to do that. These are just some examples. You could use coordinate descent. You could use what's known as stochastic variational inference. You could use automatic differentiation variational inference. I haven't defined SVI and I haven't defined ADVI. I'm just sort of saying once you have an optimization problem, you can use modern optimization problem machinery and you can get something out here. So this is just to say you can solve this optimization problem once you've set it up. And so now what we want to spend some time doing is we want to spend some time saying, hey, does this even work? You know, this mean field assumption is pretty strong, this factorization assumption. Certainly we would never want to make it about our actual model that we would have this factorization assumption. And so we want to ask, is this a reasonable assumption? Does this ever give us anything useful? And we're going to spend a little time basically looking into that right now. Okay. So let's start with some examples. I'm going to start with a simple sort of, like very simple two-dimensional example that's so simple specifically so that we can actually look at what's going on, that we can actually view what's going on. And then I'll move on to some real data, more complex examples that I think are more representative of what you would encounter in real life. Okay, so particulate matter is actually a super important and relevant application area, even if the example we're going to look at is pretty simplistic. So here what we're going to be looking at, we're going to be looking at so-called PM 2.5. So this is a big deal in terms of air pollution. It has been for a while. There's also reason to suspect that PM 2.5 particulate matter might interact in some way with COVID, and so we care about it for that reason as well, but really it's just a big deal on its own. So PM 2.5 means the mass per cubic meter of air of particles with a size or diameter generally less than 2.5 micrometers. It's also known as fine particulate matter. It's 1/400th of a millimeter, and this picture that we're seeing here is Bangkok, and you're just seeing that, you know, there are a lot of cities in the world that have some amount of air pollution, and this is something that we'd like to understand what is the amount of PM2.5. So we might collect a bunch of sensor readings of log of the concentration of PM2.5 in the atmosphere. So let's imagine that's our data here. So we have N, capital N sensor readings, Y1 up to YN. Y is again just our collection of data, all of our data. And what we're doing is we're trying to figure out something like what is the actual PM2.5 concentration at wherever our sensor is. And maybe we also don't know what our sensor's noise is. Maybe it's a noisy sensor and we'd like to learn that as well. And so that's what this model encodes. So here, theta, our parameters, our unknowns, are exactly this. We don't know the mean of PM2.5, which we imagine is the sort of actual concentration of PM2.5 at this location. Let's call it mu. And we don't know the noisiness of our sensor. Let's call that sigma squared, the variance of our sensor. And so our model, our likelihood is what type of data would we get out if we know that our sensor, say, is normally distributed in its noise, if it has some mean of mu and some variance, sigma squared. And so we would like to know that mean and variance. Now, I said here we're not going to focus so much on choosing the model. We could spend like quite a lot of time. We could spend a whole course on model choosing. So let's imagine that a scientist came by and said, here's a reasonable prior for this model. So in particular, A naught, B naught, U naught, and lambda naught here are all constants that the scientist has told us. We know them. We know these constants. Now, something that's interesting about this model is that this is what's called a conjugate prior. So you could actually take this prior and this likelihood, and I think it's a really good exercise if you don't immediately know how to do this, to find the posterior. You can write this posterior in closed form. And so I want you to just take a second and think, wait, I thought the whole point of this talk was to figure out what is our approximate posterior. So why are we looking at a problem where we know the exact posterior? Does anybody have any thoughts about that? Why would we look at a problem where we can actually calculate the exact posterior in closed form? Okay, so I think there's a point in the chat, and I think this is what this is getting at exactly. It's validation. So at the end of the day, I'm going to run my algorithm, my approximate Bayesian inference algorithm. Maybe it's variational Bayes, maybe it's something else. You know, it doesn't matter for the moment. Just suppose it's some approximate Bayesian inference algorithm. If I don't know theoretically that it always returns exactly the right answer, how do I know that it returned the right answer? And so one way to get around that is to know the answer and then check against the right answer. And so this is a case where we know the exact posterior, and so we can check if our approximation is good. And I think something you want to be thinking in the back of your mind is, well, eventually we're not going to know the exact posterior. I mean, that's the whole point, right? Is to use this in cases where we don't know the exact posterior. And so just be thinking in the back of your mind, well, how are we going to check that? Or do we need to check? What's going on there? Just keep thinking that. Okay, but in this case, we can check. And that's specifically why we've looked at this problem, is it's a case where there is a ground truth. So we're going to look at that. Now, something I'll just mention, you know, I'm not going to go through derivations here, although I think, again, this is a useful exercise to do in sort of the privacy of your own home later. And if you do some of the derivations that we're going to run through here, it's much easier to work with, instead of the variance, 1 over the variance, which is known as the precision. And so all I'm going to do is I'm going to take this exact same model and I'm going to replace all the variances with 1 over the variance for the precision. So this is exactly the same model, it's just slightly reparameterized. It just turns out that pretty much everything in life is easier to do with a precision, or at least many things. And so this is just sort of a tip if you find yourself working with this later. Okay, so here is a really important exercise. If you do no other exercise, do this exercise. You should check for yourself that this model, the model itself, the prior together with the likelihood. So here, the probability of mu and tau given y, that's exactly the joint, the prior times the likelihood. Or sorry, this is the posterior, but for the purposes of this exercise, it's the same as looking at the joint. You want to check that the joint does not factorize. It does not satisfy the mean field assumption. So because it doesn't depend on y for this purpose, we just want to make sure it doesn't factorize across mu and tau. You can look at the joint, you can look at the posterior. You can look at whatever you want. You'll find the joint is easier to work with. But it doesn't satisfy the mean field assumption. So again, we're not making this factorization assumption on the model. We're making this factorization assumption on the approximation. And so that's a really important distinction. And so again, if you do no other exercise in this talk, I strongly, strongly encourage you to do this one, or make sure that you are convinced that this is true. Because if we had to make this mean field assumption on our models, we would not be able to use any interesting models. It would be super boring models. So it's only on the approximation. Okay, so this is the approximation we're making. This is all kind of vague. We're going to see an actual illustration of this on the next page. But here what we're saying is that, remember, we're making this mean field assumption on our approximation. We're saying that our approximating distribution Q should factorize as a distribution over mu times a distribution over tau. And so that leaves off a lot of distributions, including the exact posterior in this case. And so that's the approximation we're making. Now it turns out, because everything here is nicely conditionally conjugate, that you can actually solve to find the coordinate descent steps. This is a nice exercise to derive. Again, if you get stuck, you can check out Bishop's great textbook. But basically what you'll find, again, because everything is set up so nicely, is that the mu distribution, the optimized mu distribution, will be a normal. The optimized tau distribution will be a gamma. And then what happens in coordinate descent, as you expect in coordinate descent, is you just go back and forth between these, solving for sort of what are the parts that define this normal, the mean and variance of the normal, or the parameters of the gamma. And because these aren't our parameters of our model, we want to give them a special name. And so we'll call them the variational parameters. Okay, so let's see this in practice, because I think this will help a lot in terms of illustrating what's going on. Okay, so we have 2 dimensions because we have 2 parameters. So our exact posterior is a distribution over mu, the actual sort of particulate matter concentration, or the log particulate matter concentration, and tau, the variance of our sensors, or the precision of our sensors. And so here, because again, this is a case where we actually have, you know, this ability to just do and find the exact posterior, we could show the exact posterior. You won't have that in general, but here we can do that. And so now what you want to do is you want to look at this and you want to say, okay, well, I got to start my approximation somewhere. And, you know, if we were really focusing on how to optimize things and really focusing on the optimization algorithm, we would want to spend some time thinking, how do we actually initialize this approximation? What's the best way to do that? But in this particular case, I'm just going to say this is how we initialize our approximation. But our approximation is also a distribution over mu and tau. Okay, so now what we're going to do is we're going to do coordinate descent. And first, we're going to optimize in the mu direction. We're going to optimize the mu distribution. So here's my question to you. What's going to change about this picture when I do coordinate descent in the mu direction? My first, let's break this down. My first question is the green thing going to change, or is the blue thing going to change? Exactly, everybody's right. It's blue changes. So green is the exact posterior. It's not going to change. It's just, it is what it is. And we're trying to make blue, the approximation, in some sense, be closer to green. We want it to be as close to green as possible, really. And that's what we're setting up by making this minimization problem in some sense. Okay, so blue is changing. Everybody got that right. So now what's going to change about blue? Does anybody have any thoughts about that? Great. Okay, so everybody's saying shift to the left. That's exactly what's going to happen. So the first thing that we want to notice is that definitely this is going to shift to the left. And also what we're seeing with blue here is that it is expanding. And so there are 2 things here. So one is we're doing coordinate descent. We're changing in mu before we change in tau. And so the only thing that can change is sort of the horizontal axis of this distribution, because we're only changing the mu part of the distribution. And now, because the whole idea here in coordinate descent is that we are trying to get closer to the green, then we should see that the blue kind of gets as close to the green as it can while making horizontal changes. And that's exactly what we're seeing. So it's shifting to the left because green was to the left, and it's expanding to look more like green. Okay, so now let's say we do another step, and now we're doing an update in tau. So now what's going to change about the latest picture that we saw? Great. We're going to see blue again change. Again, like green is just fixed. It's just ground truth. Nothing's going to change. And we're going to see it change vertically because now we're only changing in the tau direction by the nature of our coordinate descent. And it's going to expand vertically so that it looks more like the green. So it's going to shift vertically and it's going to expand vertically. So both of these things are going to happen. And that's exactly what we see in this next step, that again, nothing has changed horizontally because we haven't changed anything in mu, just because we're doing coordinate descent here. And now we're doing this expansion so that blue looks more like green. And then if we were doing coordinate descent, we would just keep doing this over and over again until eventually we reach some sort of stopping point where things aren't moving too much anymore. And this is what we would find in this particular problem. So a couple of points about this. So one, we have focused on coordinate descent in this particular case, but this is the kind of thing that you would expect from any optimization problem, in the sense that you're going to have a blue distribution that's your approximation to your exact posterior. It's going to get sort of closer to it, at least locally, because a lot of these optimization algorithms are local, and so that's something to keep in mind. But at least locally, it's going to do the, this getting closer to the exact posterior. And then you're going to find at the end that, there's some sort of stopping criterion, things are sort of not changing too much. And then you have your approximation at the end of that, which is sort of the distribution at the end of this procedure. And in this case, it looks like surprisingly good. I mean, this red distribution is certainly not exactly the green distribution. But it seems like the, it captures aspects of that. So, we want to be really careful in our wording. So there's a few things that are means and variances at this point. There's parameters that are interpreted as mean or variance parameters. And then separately, there's the posterior we're seeing here, and it itself has a mean and a variance. And so if I talk about the second thing right now, and I say, hey, this is a posterior, it looks like the mean and variance in each direction of the red thing kind of, isn't that far off from the green thing. Now, as we said, this is a case where we are looking at, basically a very simple problem. It's only in 2 dimensions, with very simple data. And so we really want to ask ourselves, well, what does this look like in an actual complex problem with data that's, really meaningful, and where you really want to do approximate Bayesian inference? Because there is some issue that, like, the cases where you do exact Bayesian inference, where you can do exact Bayesian inference, might themselves be sort of biased examples of Bayesian problems. And so let's look at a problem where we really want to do approximate Bayesian inference with some real data. So this is an analysis that's due to this awesome economist, Rachel Meager. If you're interested in microcredit, so microcredit is these small loans to individuals in impoverished areas, and the hope is that it helps bring people out of poverty. And then the question is, does that really happen? So if you're interested in microcredit, I really want to direct you to Rachel's paper. She has a few actually on this topic. I'm just going to look at a simplified version of this model so that it's easy for us to look through, et cetera. But again, if you're really interested in the microcredit question, I'll encourage you to check out her papers. But the reality is, this is real data. It was collected from 7 different microcredit trials by various experimenters in a number of different countries. So each trial was at a particular site in these countries. And then people want to ask, okay, I have all this data from these different countries. Is microcredit effective in general? And so the data consists of data about a number of businesses, let's say NK in the Kth site, which also happens to be in the Kth country. The number of businesses range between 900 and 17,000 per site. And then the model that we're going to consider here is, we want to say, well, does microcredit increase profit, for instance? That's sort of a well-defined question. And so we're going to look at the profit of the nth business at the Kth site. And so here we can call the profit y sub kn, again, for the nth business at the Kth site. And suppose that the profit is normally distributed around some mean that's specific to a site. So this is sort of what you would expect profit to be at a particular site if microcredit didn't exist. And now we want to understand the effect of microcredit. And so we can have a term that consists of, first, an indicator of whether or not microcredit was given. So these are all randomized controlled trials. And so it was randomly assigned to different businesses, but it's worth keeping in mind, we know the random assignment. So you treat this essentially as a covariate. So you know whether or not this particular business received microcredit. So it's 0 if it didn't, it's 1 if it did. And now this tau k is a parameter very much of interest. It's essentially how much does microcredit influence the profit at this site. And a priori going in, it could be positive, it could be negative. Maybe microcredit hurts people, in which case we want tau to be able to be negative. It could be 0. And then there's some unknown noise for this particular site. And so we can call that sigma k squared. Okay, so now we don't know mu k, tau k, and sigma k squared. So they're all going to be parameters of this model. And so what we can do is we can put priors and hyperpriors on them. Again, I wouldn't pay so much attention to all the details of this model. What's really important here is just that this is a model. It has some unknowns, that those unknowns will tell us about microcredit, and we're interested in learning about their posterior. So here, one potential thing we could do is we could say we have a normal prior. So for each site, there's the sort of site-specific profit without microcredit, and then the effective microcredit. And then we'll say that's normal around some global profit mu and some global effective microcredit tau. So if there was only one parameter that we cared about in this model, it's probably tau without a subscript, because that's like the global effective microcredit. Maybe it's helpful, maybe it's not, we want to know. And this normal model lets these things take on negative values or zero values or positive values. And then C is some unknown covariance. Okay, so again, we don't know the sigma squared. We can put a gamma, an inverse gamma on it. We don't know mu and tau. We can put a normal on those. And it turns out that the separation in LKJ prior is a nice prior to put on covariances. And again, I won't get into that, but it's a cool thing if you're curious. Okay, this is all to say now we have a model, and it has many parameters, or at least many more than the previous slide. So now you have mu k and tau k for every site. So that's already 14 different parameters. You have mu and tau, you have all the parameters in C, you have sigma squared across every site, sigma k squared. So we have quite a few more parameters, and certainly we can't just plot our posterior anymore. We're gonna have to look somehow individually at means and variances of these different posterior parameters. Okay, and so what we're going to do is we're going to run variational Bayes to get our approximate posterior, and then we're going to report posterior means and variances, approximate posterior means and variances for each of these parameters. And so a first question we want to ask ourselves is, do we need to check the output? If I just ran variational Bayes and I told you that the mean effective microcredit was 5, or like $5 US purchasing power parity, imagine it's in the correct units. Do you trust me? Okay, I hear a no. And this is the reality. We don't have a proof right now that this is definitely giving the right answer. And so at least it seems like we would like to check the output. We would like to check if this is going to be doing the right thing. And so immediately the next question is, well, how do we check the output? Because now we don't have access to an exact posterior. You can check this for yourself, but this is no longer a conjugate model where you can just calculate everything in closed form. This is a real problem where we really need approximate Bayesian inference of some form. And so I'm going to tell you what I'm going to do for the moment, but perhaps you can be thinking in the back of your head, what else could you do? What I'm going to do for the moment is I'm going to say, let's compare against Markov chain Monte Carlo. If they agree, then at least it seems more likely that they're both right. This is another approximate Bayesian inference algorithm. It pretty much, operates on a completely different mechanism than variational Bayes. And if they don't agree, well, there's a lot of checks for Markov chain Monte Carlo. And so at least if it's run long enough, there's reason to trust it. But then it's tough. Like, how do we know that this is working? Okay, so anyway, that's what I'll do in the meantime, but it's an interesting question that we'll have to revisit and keep coming back to. Okay, so what I'm going to do here is I'm going to say I'm going to run mean field variational Bayes for all these different parameters, to get my approximate Bayesian posterior, and I'm going to run Markov chain Monte Carlo, and here I'm treating it as sort of a ground truth. And then we're going to compare, in this case, let's say the posterior means that we get from each of them. Now, running, in this case, Markov chain Monte Carlo with modern automatic software for this problem takes on the order of 45 minutes. Whereas mean field variational Bayes optimization takes way less than a minute. And so this is why we'd like to develop variational Bayes. It's so much faster, and that can make a huge difference, especially as we get into larger problems. This isn't even like that large of a problem yet. But this is why we'd like to get beyond it. And I think the question in the chat is really getting exactly this. If we use MCMC, then what's the point of approximating? I don't think you missed anything at all. I think this is exactly the question that I'm getting at. We don't want to be comparing to MCMC in general. Now, I want to be clear, MCMC is also an approximation. So it's more like if we use MCMC, what's the point of an additional approximation, right? Yes, exactly. Like we need to ask, how do we get to an additional approximation where we can trust it, you know, where we know that we're getting an answer and we don't have to compare it to MCMC, because as soon as you run MCMC, you've got the cost of MCMC. So absolutely, I think this is exactly the question we want to be answering. But we haven't answered it yet, so let's compare to MCMC for now, because for various reasons we might trust its output in this case. And this looks good. So here we're seeing that the mean field variational Bayes means, the posterior means returned by mean field variational Bayes. We get one vertical coordinate for each parameter. And we plot the horizontal coordinate as the mean returned by MCMC, and these agree. These agree really well. And so this is looking pretty good. It's looking like we're getting some good results here. Okay, let's look at some more real data examples. So here's one from Criteo released this very large data set about online ads. So they're interested in something like conversion prediction. So if a customer clicks on an ad, do they then buy a product or join an email list or something like that? And a very common thing we might also be interested in is how predictive of conversion are different features, like maybe different parts of the ad. Now, you know, even if you're not interested in online ads, this is a very common type of problem. You know, you might be interested in forestry and saying, oh, we really want to understand what's parts of the forest are maybe at risk or have different types of leaf cover, and we want to know how predictive various features are of that. So many problems form this kind of thing where we want to do some kind of prediction, we want to do it well, but we also want to understand how features, you know, are involved with that prediction. And so a common model here, especially if we want to have some kind of understanding and interpretability, is a logistic generalized linear mixed model. This will let us tell us sort of, you know, how our features are, influencing our output. Now here's the rub. This is actually a huge data set. You can easily get into the millions, if not billions, of data points. And MCMC just cannot handle that. It's really beyond something that you would run in a reasonable amount of time. And so we're going to take a subset, just 62,000 data points in order to compare to MCMC. But, you know, already we're seeing the issue, right? That like you can't even run MCMC at the sizes of data points or the numbers of data points that we would like to run. And so we're seeing certainly why we'd like to get beyond it. Okay, so let's look at this Criteo online ads experiment. Now, before we get into comparing mean field variational Bayes versus MCMC here, I want to start by saying, you know, something you might have been thinking this whole time is, why don't I just use MAP? So let me remind you, so MAP is a maximum a posteriori estimate. On its own, it's just going to give you a point estimate. It's just going to give you a particular value of the parameters theta. You could use it with Laplace to get an uncertainty as well, but let's just look at the point estimate for the moment. Now, the thing about MAP is you're just maximizing the posterior and the parameters. And so it's completely equivalent to maximize the joint distribution between the data and the parameters in the parameters, because Y doesn't come into that maximization. And that's just the prior times the likelihood. So here you don't have to deal with the normalizing constant at all. You just maximize this function. And so that's like super easy to do. It requires like very little work on the part of the practitioner. It requires extremely little computation. Here it just takes 12 seconds. It's super fast. So why don't we just use MAP all the time? Well, there are various reasons that you might care about the posterior mean. So let's suppose that you do. Now, in this particular case, what we're going to do is we're going to do a similar thing that we plotted on the last page. So first, we're going to look at all the global parameters except for this one called tau. On the horizontal axis, on the left, we have the MCMC, the posterior mean returned by MCMC for each of these parameters. And on the right, or sorry, on the left, but the vertical, we have the MAP estimate. Now, of course, a mode is not the same as a mean, and that's basically what we're going to be illustrating here. But suppose you wanted to use MAP to try to get at the mean. Well, these are like, some of these values are kind of okay. One's a little bit off. But now let's look at tau. There's this global parameter tau that sort of controls essentially the local parameters, as we're going to see in a moment. And you can see that MCMC estimates its posterior mean to be about 0.8, and MAP estimates its point estimate to be about 800. So that's, you know, a few orders of magnitude off. So if you really cared about this value, you're pretty far off. And actually, more to the point, it turns out this controls, again, the local parameters, things like maybe how effective are the different advertising agencies or the different types of ads. And as a result of getting tau off, we see that MAP basically just gives all the local parameters the same value. And so they're just completely off. There's no difference between them, whereas MCMC clearly sees a difference between that. And if you want to get that information, you're just out of luck with MAP. And so this is also say that like MAP doesn't seem to be getting at what we want if what we want is things like posterior means. Okay, well, let's try mean field variational Bayes. In this case, it's actually not much more expensive. It's only 57 seconds. That's not too bad. And it turns out it just gets everything really well. So here we're seeing all the global parameters, which we can finally plot on the same scale because there isn't one that goes off by orders of magnitude. And so we're seeing the mean field variational Bayes approximations of the posterior mean compared to Markov chain Monte Carlo approximations of the posterior mean. And these look really good. They're very close. We're seeing the mean field variational Bayes approximations of the posterior mean for the local parameters as well. And again, they're very close to the MCMC approximations of the posterior mean. And again, why don't we run MCMC? Well, again, it struggles even beyond this data set, but even for this data set, even for just 62,000 data points, it takes on the order of 6 hours. And that's already just much longer than MAP or mean field variational Bayes. Okay, so this is pretty exciting, right? We're seeing, we wanted to find a method that was fast and accurate, and certainly MAP doesn't seem to be very accurate here if what we care about is posterior means. And at least in these examples, so we've gone through 3 examples now, mean field variational Bayes seems to be very accurate empirically at getting posterior means versus MCMC. So we're using MCMC as ground truth here. And so that's pretty exciting, and it's much, much faster. And I think it's actually pretty amazing that you can make this extremely strong mean field variational Bayes assumption, and yet you can get out what seems to be some pretty good approximations in cases where these are very complex models and they have complex dependencies. Okay, now before we go on, I just have to say, we're still talking about like why use mean field variational Bayes. So we already see that there are some cases where empirically it seems to give good point estimates. We are checking it in some way, and the only way that we could think of so far is to look at exact posteriors or like an MCMC approximation. And if you can think of anything further, that's the kind of thing we're thinking about in the back of our minds. But while we're talking about why use mean field variational Bayes, I think that the elephant in the room is topic modeling and topic discovery. So there's this just extremely influential model called latent Dirichlet allocation. And the idea here is that you have a huge corpus of text. Text is just ubiquitous these days on the internet, but also just in terms of like the text that people are generating at their jobs, the text that people are generating in medical applications, the doctor's offices, and so on. And so there's so much text these days, and we want to be able to make sense of it, to understand what are the themes, the topics in it. And latent Dirichlet allocation does that. And I feel like just every time I turn around and then look again online, it has more citations by like a ton. And I think I looked yesterday or something and it had over 33,000 citations, but maybe tomorrow it'll be 34,000. I mean, this is just an incredibly influential model. And so if there was literally nothing else that mean field variational Bayes was used for, this would already be enough to make it, just extremely influential, something that people are just using very widely. Okay, so we've talked about why to use it. It seems like empirically in a number of cases, it works well, at least according to our notions of working well that we've explored here. And now I want to spend a little time thinking about, okay, well, can we trust it in general? I mean, as there was this great point in the chat, we don't want to run MCMC every time. I mean, we can't, we literally can't. We've already talked about these data sets that are just much bigger than we can handle, typically with MCMC. And you can make a special MCMC algorithm for every new thing that comes along, but it would be really nice to just have something that runs really fast at scale that you can trust. And so the question we want to ask ourselves is, well, can we trust this? So based on what you've seen so far, do we know that every time mean field variational Bayes or variational Bayes in general returns some posterior mean and variance approximations, do we know that those are correct? Okay, so let me narrow that question down. Let's suppose that I show you a posterior variance approximation from mean field variational base, let's say. Would you trust that based on what we've seen so far? What have we seen so far to support a posterior variance approximation being good or bad? Have we seen anything? Yeah, I guess we haven't. I mean, we sort of have. We saw that 2-parameter model. So if we go back to the PM 2.5, we actually did look at like the full distribution there instead of just a point estimate. But you'll notice that when we talked about the microcredit example, or when we talked about the Criteo example, I actually didn't show you posterior uncertainties. I didn't show you posterior variances. I actually just showed you posterior point estimates, the means. And so we actually haven't checked on the quality of posterior variances in any of these cases, sort of the width of the posterior. And that's really important. We really care about that because, you know, if you're going to say, hey, I need, you know, I'm going to invest in microcredit, and I think that it raises incomes by, you know, $1,000 US purchasing power parity every week. That sounds really great. And is it 1,000 plus or minus 1? In which case, yeah, like we know that it's really helping people. Or is it 1,000 plus or minus 10,000? In which case, maybe half the time it bankrupts people, and maybe that's not a really good thing that you want to be investing in. Okay, so let's see if we can actually get these variances right as well, these uncertainties, which we motivated in the beginning with all of our applications. There are lots of applications that care about uncertainties, so let's talk about uncertainty. Okay, so here we have the KL divergence. This is just reiterating what is the KL divergence that we're optimizing. So it's the particular direction used by variational Bayes. And we have our assumption, our mean field variational Bayes assumption written out, this factorization assumption, that this Q factorizes over these little components, theta j. Okay, so let's consider, again, a super simple example. It's an exact Gaussian. So suppose my exact posterior, my 2 parameters are theta 1 and theta 2, and my exact posterior is a Gaussian. Why would we even care about an exact posterior that's a Gaussian? Well, there are a couple of reasons. So one is in conjugate linear regression, you're going to get a Gaussian. Now, of course, again, we're not going to use approximate Bayesian inference in a conjugate problem, but there are a lot of problems that are close to conjugate linear regression, and maybe we expect that they have a somewhat similar geometry. Another example is that there's this thing called the Bayesian central limit theorem. And it says roughly, and you have to be a little bit careful here, but roughly as I get more and more and more data about a particular parameter, the posterior over that parameter is going to look more and more and more Gaussian. And so for all of these reasons, we think that Gaussians or shapes like Gaussians come up reasonably often. And so this is not like, you know, a totally made up example. This is kind of a realistic shape that you might encounter in real life. And of course, it would be higher dimensional than 2-dimensional, but you'll see that the conclusions we make here apply to more than 2 dimensions. Okay, so this is a case where if you're clever and use the precision, you can very easily derive the mean field variational Bayes coordinate ascent step. So here I'm saying coordinate ascent, I'm saying that as CA. I said coordinate descent earlier, it's just how you think about it, right? You're minimizing the KL, but you're maximizing the ELBO. So, you know, you're doing coordinate something. And of course, you don't have to optimize in the coordinates, but here you can do it very easily. And in fact, you can go beyond that. Once you've derived these steps, you can actually derive exactly the mean field variational Bayes approximation. You don't even have to iterate. You can just write it down. And I think this is another really nice exercise to do. Just make sure that you can write this down. You can figure out what is the exact mean field variational Bayes approximation. No optimization algorithm needed. You just write it down. And this is it. This is the mean field variational Bayes approximation here. And so the mean, actually, the posterior mean is exactly right, the approximation for the posterior mean for mean field variational Bayes, but you can just immediately see that the variance, you know, the width of the distribution is way off. The width of the green thing is way larger than the width of the red thing. And the red thing is meant to be approximating the green thing. So we get these underestimates of variance, that's actually sort of like the worst direction, right? Because if you are saying, hey, I want to be really careful and conservative and not rush into a decision, that's like the opposite of what you're saying here. You're saying, oh, I'm super confident, I'm going to invest a ton of money in microcredit, or I'm going to invest a ton of money in this other thing, even though I don't really know enough to maybe do that yet. So you're sort of rushing into decisions as a result of this. And in fact, you can be sort of arbitrarily overconfident just when the exact posterior is very correlated. And the issue is that you don't know the exact posterior. So it could be very correlated and you just don't know because, again, you don't have access to it. This is sort of the only information you have about it. And so if you only saw the red thing, you might think, gosh, I'm super certain about what's going on. I have very little uncertainty, when the reality is the green thing, and perhaps you should have a lot of uncertainty. And then, of course, by construction, you don't get covariance estimates because you're making this factorization assumption. And so you can't get covariance estimates. And so let's see how this comes up in real life. So let's look at this microcredit example again. So before, I had a point for each parameter, and for each parameter, I plotted the MCMC estimate of the point estimate, the mean, and the mean field variational Bayes point estimate of the mean, and we compared them. And so let's do the same thing now, but for standard deviation. So here, again, for every one of the parameters, we have a point. Its horizontal value is the MCMC estimate of the standard deviation, the posterior standard deviation for each parameter. And the vertical value is the mean field variational Bayes estimate. And you see that there's this x equals y line, that's in black. And so mean field variational Bayes is systematically underestimating uncertainty. Now, it turns out it doesn't have to underestimate uncertainty. It can overestimate it as well, but that's kind of even worse because you just don't know what's going on. And in general, we tend to see empirically that it underestimates uncertainty. And this has a real empirical consequence. So suppose that I'm interested in tau, again, the microcredit effect. How much is microcredit helping people, if at all? And I find perhaps that the posterior mean is something like $3 US purchasing power parity every 2 weeks. So it's helping people, it's positive. And then maybe I find that the standard deviation is 1.83 US purchasing power parity. And so the mean is 1.68 standard deviations from 0. Now, something I might have done is I might have gone into this problem saying, hey, if the mean is positive, the mean effect, how much is microcredit helping profits? If it's positive and it's more than 2 standard deviations from 0, and it's like substantive enough, that it's really helping, then I'm going to invest in microcredit. I'm going to, go out and make this my cause, and I'm going to, really, really make this happen. And here I find that, in fact, the mean is not 2 standard deviations from 0. So I'd have to either gather more data or try to understand, are there certain covariates of households that influence whether microcredit is effective? I'd have to go back to the drawing board and do some more social science. But here, what's going to happen if I use mean field variational Bayes is I'm going to underestimate the uncertainty. And because I underestimate it, I'm going to erroneously think, I'm going to make the error of thinking that the mean is more than 2 standard deviations from 0, and I'm going to rush into a decision that is not warranted by the actual Bayesian posterior. So to the extent that we trust the Bayesian posterior, this is just giving us a different answer, a bad answer. It's not giving us the actual Bayesian posterior. And in fact, we see this in other areas as well. So this is the Criteo online ads example. And here, again, we're looking at standard deviations rather than means this time. And for each of our parameters, we're seeing that mean field variational Bayes is very much underestimating the standard deviation, the posterior standard deviation. If we think that MCMC is doing the right thing, and there are various checks that make it likely that it is here, then it seems like mean field variational Bayes is just off, that it's just not, getting these correctly. Okay, what about means? We've talked about standard deviations now. But do we know that mean field variational Bayes gets posterior means right? Well, let's think about what we've done so far. I've shown you 2 empirical examples. I've shown you the posterior means being correct on the microcredit example. I've shown you the posterior means being correct on the Criteo online ads example. And we showed also this sort of almost toy example of PM 2.5, the particulate matter. And so I guess the question, the sort of meta question is, if I show you 3 examples of something working, does that mean that it works all the time? And hopefully the answer is clear that it is not a proof that it works all the time. I mean, it's certainly some evidence that it's useful, but it's not a proof that it works all the time. And perhaps we might look at some examples where it does not work all the time. And so this is a model for relational data with covariates. So relational data is like data on a graph. Bailey Fosdick does some really excellent work in studying graphs and networks. And of course, we have giant network data nowadays. You know, you look at social networks, but also environmental networks, transportation networks, and you can easily get more than 1,000 nodes. But again, there's this issue that if you have more than 1,000 nodes, Markov chain Monte Carlo takes forever. You don't want your algorithm to take more than a day because you're going to have to iterate on this algorithm, and it's going to take a while. And so here again, we're looking at mean field variational Bayes, estimates of posterior means versus MCMC estimates of posterior means. And it seems like they're not quite on that x equals y equality line. And in fact, we can look at particular parameter values here and look at 95% credible intervals. So this is a little bit different than what we've been looking at now. Before we were looking at sort of variances, but if something isn't symmetric, you might want to look at credible intervals. So where is 95% of the mass in your posterior, and that's what we're seeing. So the point is a point estimate in black here for each parameter on the horizontal axis, and then the vertical is the line is the 95% credible interval. And what's interesting is you're seeing that mean field variational Bayes means estimates are sometimes outside of the 95% credible interval. And so that's problematic, right? Because if you're using this to make decisions, then that suggests that you would make a different decision, that your mean really is outside where the range of values that might be an acceptable place for that mean. If you assuming you care about the Bayesian posterior. Okay, and now another question we might ask is, well, maybe there are certain types of problems that mean field variational Bayes is good on and certain types of problems it's not. And so if we just knew those in advance, we could just, you know, sort of apply mean field variational Bayes only to those types of problems. And so let's suppose that we want to predict some measure of performance in college, at university. So like grade point average is a common measure of performance for an individual. So let's say N indexes an individual. And then maybe in order to do that, we might collect standardized test scores, like maybe some kind of test people took in high school. So there might be some tests that are common across our population. So like if we had a US population, at least before this year, SAT and ACT might be an example of that, but it could be some other population. But it's often the case also that there are regional test scores. You know, even if we had a global population, there'll be regions, you know, certain countries have their own tests, and so we might want to take those into account as well. And so we might come up with a normal model where there's some linear component specific to like a general test scores, and there's some linear component that varies by region. And so it's indexed by KN, which is, let's say K is the region. Okay, and then we have some priors, and this is all to say this is a model. This is a model with parameters we're interested in learning that we have some posterior over. And so what we can do is we can simulate data from this model. So we know that there's no model misspecification. Our data is exactly from the model that we are specifying, so we're not even messing around with that. We get 3 data sets. Each has 300 data points. And now we're going to plot the MCMC mean estimate of a particular parameter for each data set versus the mean field variational Bayes mean. And so we have that here. And this is across data sets for the same parameter, whereas before we were plotting for a single data set, different parameters. So it's a little different from before. But based on this, you might think, gosh, mean field variational Bayes works well for this type of model because look, the means agree between MCMC and mean field variational Bayes. But now suppose I simulate data from, you know, 100 different data sets, and I find that a lot of the means now don't agree. And so it doesn't seem like I can just conclude in this particular case, you know, that this model is good for mean field variational Bayes. Okay, so I'm gonna leave off here. I'll just finish up on this slide. I think we want to ask, what is the issue? In particular, here are your options. It could be my implementation. Maybe the implementations that I used in these examples are bad implementations. You know, maybe there's a bug in the code somewhere. Maybe it's my approximating algorithm. Even if my implementation is exactly correct, we know that optimization is a little challenging. Maybe I just used a bad optimization algorithm. Maybe it's the mean field part of mean field variational Bayes. Maybe it's variational Bayes, maybe it's something else. And so this is where I want to leave you with a question for next time, because we'll take up this question again next time. What is it? Can you rule out, based on the information that we have right now, whether the implementation is the issue? Could that possibly have always been the issue? Could mean field variational Bayes always give you the exact correct answer, but it won't, of course, if there's a bug? Can you rule out the algorithm? Can you figure out at what level this issue might be at? And so I'll just leave you with that question to think about for next time. Again, all of the slides will be distributed to you. They'll also be up at my website. And I really, really encourage you to think about some of the exercises in the meantime, because I think that will be helpful as well. Okay, great. I'll leave us on that cliffhanger, and I believe I will catch you 2 days from now to talk more about where we have left off. Thanks very much. So we've been talking about scalable Bayesian inference, and we're going to continue that today. And I just want to reiterate this point from the previous lectures that already I believe the organizers have shared with you the PDFs of the slides from the previous 2 lectures. They're also at the link below. So hopefully you have access to all of that. And I just think if you haven't already, I strongly encourage you to work through a few of those exercises from the previous lectures. I think it really helps cement and help your understanding with these things to really engage like that. Okay, so let's recap, because it's been a few lectures and it's actually been a couple of days now since the last one. Remember at the very beginning of the very first lecture, we spent some time motivating, why do we care about scalable Bayesian inference? And in particular, we went through a number of real-world examples in extremely sort of important and time-sensitive, especially in the case of things like COVID, but also other things like, finding a lost airplane and, fishery management and all of these other areas, but also, generally science and technology. People are using Bayesian inference. They're using it in these very fundamental scientific, engineering, social science advances. And in particular, the things that they're reporting, we saw in a lot of these applications are generally, there's some unknown or set of unknowns that they're interested in, and they want to get a good estimate of what that unknown thing is. Generally, we've been calling that the parameter. And they want to get an uncertainty too. It's important not just to know, what do we know, but how well do we know it? There's a very big difference between saying, hey, we think that the effect of microcredit is it raises people's profits by something like, $100 US purchasing power parity every week. There's a big difference between 100 plus or minus 1 and 100 plus or minus 10,000, in which case we really just don't know anything. And we might not want to proceed and make big decisions based on that knowledge. And we said that a big challenge here was that we want to do things quickly and we want to do them accurately. So we said we want to do things quickly in compute time. We don't want to sit around for 6 months, waiting for our algorithms to run, but we also don't want to sit around for 6 months waiting for a biologist wasting their time deriving equations when they could have just been doing their awesome, important biology work. And of course, it's so important, again, not to talk about speed on its own. It's very easy to come up with a fast algorithm. It's very easy to come up with a fast and easy to use algorithm. It's very hard to come up with an algorithm that is both fast and accurate. So we have to talk about accuracy at the same time we talk about speed. Okay, and so we want to have this for Bayesian inference. We want to do all of these things quickly and accurately. And sort of the thing that we've been exploring, and you could do a very similar exploration for other Bayesian methods, is variational inference as a potential method for approximate Bayesian inference, something that will approximate these point estimates and will approximate these uncertainties. And we've been focusing on posterior means and posterior variances, respectively, for those point estimates and uncertainties. And so let me just recap something that we already saw, but I think sort of encapsulates some of the lessons that we learned along the way. So one of the first things we saw was that we can't just use math to solve this fast Bayesian inference thing if we care about means and uncertainties. I'll just say incidentally, you could have a really long and interesting discussion about what are the benefits of Bayesian inference? Why do you want means and variances versus, I think you very legitimately in some cases really care about medians and quantiles and things like that. And there are ways that you even potentially want to get beyond Bayesian inference. And I think these are really interesting questions, and I would say they're outside of the scope of what we're doing right now. We're assuming very realistically that many scientists are using Bayesian inference, and we're just trying to speed that up. But I think those are very interesting and important questions as well. Okay, so supposing we're doing that, supposing we want to get these posterior means and variances, we saw that map isn't going to cut it. We saw that you can just get these extremely wrong orders of magnitude off answers just using map. And so we looked at, could we use mean field variational Bayes instead, a particular type of variational Bayes, as we saw. And we saw much better results, at least for some of our application areas. So we looked at this online ads experiment. We looked at, this experiment with microcredit data. These are all real data sets and, very similar to analyses that you would do in person. In fact, you can even see Rachel Meager's paper for a more complex analysis that you would do for microcredit. And it has many of the similar flavors to what we're seeing here. So in particular, what we're seeing here is that even though mean field variational Bayes doesn't take much longer than math, it's only 57 seconds in this case, we find that the posterior means estimated by mean field variational Bayes very much align with the posterior means estimated by Markov-Chain Monte Carlo. And remember, we came across this sort of issue of, okay, well, we want to know if we're doing the right thing. How do we do that without also running Markov-Chain Monte Carlo because it's so slow? So in particular, in this case, it takes 6 hours. And not only that, but the reason that we're looking at a smaller data set here, because this is not the full size of this full data set, is in order to compare to Markov-Chain Monte Carlo. So that's just obviously very limiting. We want to just run the very fast thing, which in this case is mean field variational Bayes. And so in some sense, we want to know, can we trust it in general? Well, certainly, we sort of immediately saw a case where we pretty clearly cannot trust it, and that's in estimating posterior standard deviations or a notion of uncertainty. So we saw that this just dramatically underestimates these uncertainties in general. So here we're doing a same plot. We're saying each of these dots is one of the parameters. In the top, we split them into global parameters and local parameters. And just to reiterate, global parameters are parameters that are shared across the whole data set. Local parameters are things that are specific to data points or a data point or a collection of data points. So something like a particular advertiser or a particular ad. And so here we're just collecting some of them for the standard deviation or looking specifically at these global parameters. It's a similar thing for the local parameters, but we're seeing this underestimation. And we saw this in a variety of other cases too, right? So we saw similar behavior for the microcredit data. We saw similar behavior for the PM 2.5 sort of illustrative example, the air pollution example. You see this in many areas. This is sort of the folk wisdom about why people use variational Bayes is that the point estimates seem to be pretty decent, but it's also well known that the uncertainties tend to be pretty bad. And you can see this in a multivariate normal example. So here, we looked at an illustration where there were 2 parameters, a 2-dimensional parameter, theta1 and theta2. Here we're looking at the contours. There's only one contour, but you can imagine what normal contours look like for an exact posterior if it were normal. That's in green. And then we can look at the contours of mean field variational Bayes. Again, just plotting one contour here, but it's normal. You can sort of imagine what this looks like. And we saw that even in this 2-dimensional example, and this absolutely holds in higher dimensions as well, that you get this massive underestimation of uncertainty, and that you can make that sort of arbitrarily bad by increasing the correlation in the exact posterior. And the danger here is that you do not know the exact posterior. It could be highly correlated for all you know, and then you'd be in some hot water based on what we're seeing here. Again, we looked at lots of different examples. I want to also point out that in this nice graph network data analysis by Bailey Fosdick, we actually see that the means can be off too. And we saw some more examples of this in some simulated data. So it's not just an issue of model misspecification. This is really something that can happen, that the posterior means can be misestimated. So, so these are some of the, the minuses that we spent some time discussing yesterday, and really spending some time in a variety of sort of real data analyses and simulated data analyses, and just looking at sort of a wide range of data analyses. And so I want to start today by spending a little time digging deeper into that, understanding what's going on here. And then we're going to start talking about some solutions, but I think one of the things that's really exciting about this area is that there are definitely open problems. Now, a meta point that I think is really important to make is that I think none of this is specific to variational Bayes. I think if you look at any machine learning algorithm, it has pros and cons. If you do not know the cons, that's likely just because you don't know them. That's not because they don't exist. There's no perfect thing that works in all of the different cases. So there's no perfect algorithm. And so it's always worth spending some time exploring, when do things work and when do they not work, especially if you ever plan to use any of this stuff in practice, or if you plan to collaborate with people who are really working in practice. It's really important to know both the pros and the limitations of your algorithms. And so here we have a sense of that at this point. We have a sense of some of the benefits of variational Bayes. Definitely the speed is a huge benefit. I mean, there are some things you can just never run typical, MCMC algorithms on unless you do some very maybe special kind of algorithm. And yet we've also seen some of the cons. While it works really well in some cases, it doesn't in others. How do you know which one you're in? And so we want to sort of understand now at a more deeper level what's going on. And so that's what we're going to spend some time on coming up here. So in order to start delving into that question, let's just recall this sort of Venn diagram that we had of approximate Bayesian inference and the choices that we had made in this particular lecture, because I want to emphasize that they're choices. You could make other choices. And I think people already in the chat in these lectures have thought about some really interesting other choices. Some of them have been done already, but that doesn't mean you shouldn't brainstorm them. I mean, think about what you're thinking, come up with cool ideas, and then see if they're out there already. But the choices we made in this lecture was, first, we said, let's use another distribution to approximate our exact posterior. We don't have to do that, but that's a choice that we're making for our approximation. We said, let's use an optimization to solve for the exact posterior, not just any optimization procedure, because you could think of MAP as an optimization procedure, but we're using this particular optimization procedure where we minimize some notion of farness across the nice distributions, so that we call capital Q, and this farness is F. And so variational Bayes, one way to think about variational Bayes is that it's the particular choice of this optimization problem where we use the KL divergence in a particular direction, because it's not a distance, it's not symmetric, so we have to choose a direction. So this is one particular direction. And then a further choice is to say, what are these nice distributions? If we make this mean field assumption, this sort of factorizing assumption, and typically, really, in practice, people often make this exponential family assumption, and we get mean field variational Bayes. And then finally, we have a well-defined optimization problem at this point. We have to decide how to optimize, so we can come up with an optimization algorithm. And then finally, we have to write it down. We have to actually have an implementation and make it happen in practice. We have to code it up. And so we want to start sort of by looking from the bottom up and saying, how deep is the issue? I mean, I think a very realistic question you could ask if something isn't working is, was it just my code? Was there just a bug there? Is it possible that the only reason that we get these bad posterior uncertainties, for instance, is a bug in the code? And so this is a real question that I'm asking to you as the audience right now. Is it possible that this whole posterior uncertainty underestimation thing with mean field variational Bayes is just due to bugs in the code? Based on the information that you've seen in these lectures, can you conclude one way or the other? Anybody have any thoughts? Okay, how about this? Let's think through the examples that we've seen so far. So we saw in that Critio example that the posterior uncertainty was underestimated. That's something that, I just presented some code to you. I just said, hey, we ran this and here are the results. And so it seems totally plausible to me that could be a bug without any more information, without you having derived it all yourself and independently created it, you just don't know whether that could be a bug in the code. But how about the Gaussian example? Could that be a bug in the code? So I showed you this Gaussian example. We took a multivariate Gaussian and approximated it using the mean field assumption. And I said, this is something you could derive. In fact, I said this would be a good exercise to derive. Don't worry about whether you actually completed that exercise or not. But is it possible that the only reason that we got that under approximation, that, let's just go back to this previous slide. So here's this Gaussian example in the lower right-hand corner. Is it possible that this mean field variational Bayes approximation looks bad, looks like it's underestimating the uncertainty just because there's a bug in the code? Does anybody have any thoughts? I'm seeing some no's. Does anybody want to elaborate on that? I want to remind you a little bit more about this Gaussian example. So in the Gaussian example, I said you can actually solve exactly for the mean field variational Bayes optimum. You actually don't have to do any optimization algorithm. You don't have to, actually make any code at all. This actually isn't based on solving anything in code. You can literally write down the mean field variational Bayes optimum. You can solve exactly for the exact distribution that optimizes the mean field variational Bayes optimization problem. And so is it possible that there's a bug in the code for this one? Yeah, I guess the point that I want to make here, and I hope some of these chat answers are getting at this, is that there is no code. This is a purely theoretical example. And so every time there is code, when you get something that's unexpected, it's at least possible, at least theoretically possible, that it's due to a bug. And we should be aware of that that's a possibility. But in this case, it's not possible. I mean, there's a chance that my derivation could be wrong, but at this point, many authors have made this derivation. So David Mackay made it in his textbook in 2003. Bishop made it in his textbook in 2006. It appears in many papers. Yes, exactly. So there's a point in the chat. If we can solve it exactly, the issue is not a bug in the code. And so here, at least with the Gaussian example, we have the theory to back this up. And so it's possible that we misderive the theory, but given that so many people have looked over the theory at this point, that seems less likely, and there's no code. So there can't be a bug. So it's not an implementation issue. And so I want to rule out that every problem with mean field variational Bayes that we've seen has been an implementation issue, because we could actually solve some exact problems. We didn't have to rely on an implementation. We could actually do things exactly. Okay, so what about maybe the issue is the optimization algorithm rather than the implementation? Maybe it's not my code, but I didn't use, I used coordinate descent, and actually I would have done better to use some kind of stochastic gradient descent or something like that. Could that be the issue that gives us all these issues where we see this underestimation of uncertainty and other problems? This Gaussian example, could the issue be due to stochastic gradient descent versus coordinate descent in the Gaussian example? Okay, so I see some no's. Does anybody want to elaborate on why that is? There's some thoughts. Any other thoughts about why this might be? Remember how we're saying we derived the Gaussian example. Did we use coordinate descent? Did we use stochastic gradient descent? What did we use there? Yes, okay. In the example, we know the exact solution. So this is the really key point. It's basically the same answer as before. So the answer is we didn't use any of these things, or we didn't have to. We don't have to use coordinate descent. We don't have to use stochastic gradient descent. This is a case where we can solve for the exact optimum. And so again, it can't depend on the algorithm if we can just solve for the solution. So in all the other cases, at least a priori, it's possible. It's certainly the case that some optimization algorithms are more likely to get stuck in the local optimum. It's possible that there could be some issues, but that's not the issue here because the Gaussian example was exact. We solved exactly for the mean field variational Bayes optimum. We have this well-defined optimization problem. Typically, we're going to have to use some optimization procedure to get close to the optimum, but here we could solve for it exactly. And so we know that at least the issues that we saw in the Gaussian example can't be due to implementation. They can't be due to bugs. They can't be due to choosing different types of optimization algorithm like coordinate descent or stochastic gradient descent or anything like that, because we solved them exactly. And of course, once we have that information, it seems more likely that the other things are sort of real issues that are going on. We have at least a little bit more evidence in that direction. But this is sort of the point of theory, right? To make sure that the things we're seeing are real, to check that it's not somehow due to a bug, which is just life. I mean, we all have bugs in our code. Like it's unavoidable. And so we want to be able to check in a way that doesn't depend on that. And so this can help with that. Okay, so somebody in the chat already said they think it's this mean field assumption, and so that's what we're looking at next. So we've ruled out that it's just an issue with the implementation, that we're seeing these underestimations of uncertainties and things like that. We've ruled out that it's just an issue with the optimization algorithm, and so the next question is it just the mean field assumption? So first, I want to just spend a second saying why you might think it's just the mean field assumption. I mean, it's something we've seen all along, but I want to spend a tiny bit more time on it, and then we'll start getting into, is it just the mean field assumption? Okay, so let's interrogate this mean field assumption. Okay, is it just mean field? The MF in MFVB. So here we're just saying MFVB is mean field variational Bayes. Okay, well, let's go back to this illustration, this Gaussian illustration from before. So this is the KL divergence as we're optimizing it in variational Bayes, the direction that we're optimizing it. And this is the mean field assumption, this factorization assumption. Again, in general, you're usually assuming exponential families. In the Gaussian case, it just happens that you'll get an exponential family. But it's implicitly there. Okay, so why do we see this behavior? So let's spend just a moment on that. Well, let's imagine, take this first plot, the plot on the left, and look at that sort of lower right-hand corner. Now, if you look at this Gaussian, the green Gaussian, the exact posterior, there's just not much mass in that lower right-hand corner. There's very little mass in the exact posterior due to the geometry of this problem. Now, if you look at the KL divergence, imagine that we looked at a Q. Q is any approximation that we could use, and we're just trying to find the best Q for Q star. If you look at a Q that has a lot of mass in that lower right-hand corner, then you're going to see that we're sort of dividing a large quantity by a very small quantity. And so that could be potentially very big, especially when we have things like Gaussians with these, quadratically, exponentially decreasing tails, super exponentially decreasing tails. And so that could get very large, and then we would have this large KL, and that Q would not minimize the KL. And so from that perspective, whenever the exact posterior has very little mass, we're very much incentivized not to put mass in Q there. And so a sort of high-level way you can think about this is that somehow KL in this direction is asking us to fit our approximating posterior sort of inside the exact posterior. And so that's why you're seeing what we're seeing here. We have to find an axis-aligned distribution by the mean field assumption that sort of fits inside our exact posterior, and this is what we get. Now this is like a rough version of, there was a nice comment the first day talking about how KL has this issue where, if the supports don't align, then you could have some sort of division by 0 and so on. This is like the relaxed version of that. So it's not like we're not allowing these to, have more mass in some areas than other areas. It's that we're disincentivized for that to be the best Q. And so in general, you're going to see this kind of behavior as sort of a rough intuition. And certainly that's what we see here. And so by trying to fit that green, that axis line red thing inside the green thing, that's why you end up getting this, you know, worse and worse behavior as the correlation increases. Because how do you fit a tiny little axis aligned red thing inside this long green strand on the far right? You know, you have to make the red thing very, very small. So there's this question, will the approximations never be accurate? I mean, it's hard to say what does it mean to never be accurate, right? So certainly if this were an axis-aligned distribution to start with, the exact posterior, then this would be a perfect approximation. And certainly that's what we see. In all of these cases, the means are correct. In all of these normal cases, the means are correct. The uncertainties are very wrong, though. So in general, I think it's more of a question of, suppose you don't know the exact posterior, it's pretty clear that there's nothing that guarantees that you're going to get an accurate assumption here. And there's no reason to suspect that going in, right? I mean, this is a pretty strong assumption. You're making this, this axis-aligned assumption in your approximation. I mean, it's kind of amazing how much I think the posterior means are even accurately represented in practice. And I think that's sort of just a really interesting fact that we could probably all understand a little bit more. Okay. So this is why we might think that mean field variational Bayes somehow is to blame, right? Because we're minimizing KL, and this axis-aligned assumption is sort of making us fit something that doesn't quite fit inside our exact distribution. And certainly, if we could match our distribution, if we could say that we could have any distribution and we minimize KL, and we can get KL to 0, then we know Q and the approximate posterior, and the exact posterior are equal. The problem is that in practice, that we're specifically choosing Q to be a set of nice distributions, an easy set of distributions, the distributions that we'd like to be able to work with. And so we're never getting KL down to 0, and that's where the issues come in. And so let's just look really briefly at, there's this really cool set of research by Turner and Sahani. So here, this is just the cartoon from earlier. What are we trying to do in VB? We're trying to find the closest of the nice distributions to our exact posterior. So that's just my cartoon, but Turner and Sahani showed empirically in 2011 that you can have a strictly larger set of nice distributions, but worse posterior mean and variance estimates. So again, typically our nice distributions aren't going to be the full space of distributions. It's hard to work with that because you have to have this practicality, you have to have this speed as well. But you can make them broader. So for instance, you could allow more interactions, more correlations than a pure mean field variational Bayes assumption. You could have a little more structure, and that's what they do in this paper, and I encourage you to check it out. But being closer in KL in this direction does not imply that your posterior means are closer. It does not imply that your posterior variances are closer. And so I really encourage you to work through an exercise. I believe that you can show with a simple example that this is true, that having a smaller KL does not imply that you always have better mean and variance estimates. Okay, and so now we have somehow the same set of questions, but this is leading us in an interesting direction, but how much worse can the estimates be? Are they really that much worse? You know, maybe they're a little bit worse. Maybe they're not that much worse. And is it possible, again, that it was just the implementation? You know, Turner and Sahani did a bunch of empirical studies here. Maybe they had a bug in their code. And so we always want to ask, you know, could it have just been the implementation, or is this really some fundamental thing? Spoiler alert, the answer is it's a fundamental thing. Okay, so we're about to have a discussion that's based on what KL values do you actually see in practice? Because remember, in practice, you just don't get KL down to 0. That's not typically something we see. Maybe you all will invent some amazing new variational Bayes algorithm that really gets KL down to 0. But in practice, certainly for mean field variational Bayes, you won't see that because, again, you're strictly far away from that exact posterior. And even in all of the other methods of variational Bayes that people use, so there's some using mixture models, there's some using this more structured, you know, thing that goes beyond mean field, you don't get KL down to 0. So the question is, first of all, what does it mean to have a small KL? And so I'll just note a couple of papers. The second paper is our paper, but the first paper is a totally independent paper, that small KLs in practice, the kinds that you see by actually optimizing, are somehow around 0.5 or bigger. And so we can look at some theory let's take any constant c. And our theory shows the following, that you can have a small KL, so in particular KL value less than 0.23. So hopefully, you know, this first bullet convinces you that that is a small KL that you might see in practice. You would be pleased to see such a KL. In fact, you'd have to estimate it to even see it. And you can have an arbitrarily bad variance estimate, and this does not depend on having more than 2 dimensions. So it definitely doesn't depend on the mean field assumption. So here's a concrete example of how this can happen. Imagine that your exact posterior, so that's the P, is a student's T. Now, this is a very, very reasonable assumption, and for the following reasons. So real life often has power laws, or it often has heavy-tailed behavior. And so here I have a slightly heavier-tailed behavior than normal. Certainly that's something that people see in all kinds of real-life applications, and so that's sort of a realistic situation to be in. And we're gonna look at its variance, the variance of this, you know, very simple proposed exact posterior. Let's call it sigma squared P. Now, we're going to use as our approximation a normal, a Gaussian. For instance, if you use automatic differentiation variational inference, basically that assumes a Gaussian approximation. This is a really common approximation to make. And so again, I think this is somewhat representative of what you might see in practice, but in a super simple distribution. So if things go wrong in the super simple case, then we'll be worried about the more complex realistic cases. Okay, so we're going to approximate the student's T with this Gaussian, and we're going to look at their variances. So we can look at the variance of the student's T, and we can look at the variance of the Gaussian. And we can show that just by increasing the variance of the student's T, we can make it so that our actual posterior standard deviation is arbitrarily larger than our variational Bayes approximation. And the KL is small. So here's the point that's going on here. You come back to, you know, your person studying microcredit, your practitioner that you're collaborating with, and you say, hey, the posterior variance, you know, is this microcredit effect is $100 plus or minus 1. So we feel very comfortable, like we're super sure that this is really helpful. We know the value of how helpful microcredit is, and we're going to go forward with investing in it. And the observation here is that if you just said, hey, I have a small KL, and so I think I can trust this, that would not be warranted. That in fact, it could be that the actual posterior variance, like the thing that you think really encapsulates your uncertainty, if you're being a Bayesian, could be arbitrarily worse. It could be orders of magnitude worse. It could be anything. It could be, you know, as worse as you could imagine, if all you know is the KL. And so that's scary. And this is just a pure theory example. This doesn't depend on implementation. This doesn't depend on optimization algorithm. This is just, we can show that you can have this situation. Okay, and the same thing happens with the mean. So first we want to be a little bit careful about what it means for a posterior mean to be arbitrarily bad. You can just take any 2 means that are arbitrarily close as you want them to be, and then change the units so that you say they're super duper far. And so you have to compare the means on the scale of the standard deviations. That's also how you would make actual decisions in practice. You usually say something like, oh, is my posterior mean more than 2 standard deviations from 0, or, you know, something like that. And so that's really important to be on that scale. But it turns out you can also have a small KL and an arbitrarily bad mean estimate. Now this is a little bit more of a contrived example. It's still unimodal, it's still one-dimensional, but we're going to use Weibels. So in this case, we can look at 2 Weibels, we can compare their means, and we can make them arbitrarily bad. Now, this is all just to say that you can have a somewhat small KL and get these arbitrarily bad estimates. Does this mean that all hope is lost for KL? Absolutely not. It might be that if you had an even smaller KL, that you would get around this issue. But it does point to a problem. It points to the problem that having a small KL does not imply what you want necessarily about means and variances. Because if what we want is to get close to the exact posterior mean and variance, we want to guarantee I'm being close to the exact posterior mean and variance. And this just shows that at least for some types of things, you're not going to be able to get that. Okay, so is it just mean field variational Bayes? Well, it seems like at least it's not the only thing. That variational Bayes itself is implicated as well. So certainly this is not to say that the mean field assumption does not add extra assumptions. You know, it certainly adds some extra constraints. But the KL itself, the KL in this direction, clearly has some issues if our goal is to approximate posterior means and posterior variances. And we should really be aware of that we don't necessarily get a guarantee on that just by having a small KL. Okay, so we've asked, you know, when can we trust BB? And I think we're starting to get an answer that there are really pros and cons. And if anything, I would say that this is just one aspect of that. There are all kinds of other things that, you know, we could easily spend like a whole course on. We could talk about multimodality. Here we've focused on unimodal distributions. Multimodality is actually an issue as well, although that's a very subtle point because there can be pros and cons to dealing with multimodality with variational Bayes. But from a unimodal perspective, we've seen that there's some real pros and cons here, that it can have issues fitting posterior means and variances, but conversely, there are some problems that it can just activate on that you can actually use it for that you can't really even use MCMC for. So it's a real trade-off like most things in life. So we can start asking, where do we go from here? Can we improve things? Can we have even better methods than the ones that are out there? And I think this is in some sense really exciting, right? At least for people who are really interested in doing machine learning research. You know, where are the open questions? You know, what remains to be done? And I think there's a lot of open questions here, and a lot of things that remain to be done. You know, if you're purely interested in applying these ideas, I think this is all still really important. You want to know, you know, when can you apply this safely? What are the potential issues that you could run into? But I think now we're going to talk a little bit about not just, you know, getting beyond that for applications, but also what are some interesting directions for future research. Okay, so let's spend a little time on where do we go from here. So the uncertainty problem, even though it seems like the biggest problem with variational Bayes, in some sense is the easiest to solve. And so I'll mention, you know, here we saw, this is sort of the same illustration we saw earlier, but with more, you know, just more contours added to the contour plot. So we have our exact posterior, it's a normal, and we have our mean field variational Bayes approximation. We just see that it's underestimating the uncertainty. But something that you can actually do here is completely correct the uncertainty with this method that we have called linear response variational Bayes. And I also want to point out this early work by Opper and Winther in 2003 that really, you know, precipitates a lot of these ideas. There's obviously less focus in 2003 on modern tools that make this easy, like automatic differentiation, but it's a very, very cool paper. And the procedure is, in some sense, very simple. You just run any type of variational Bayes. It could be mean field variational Bayes, but it could be, you know, anything else. There are certainly other types of nice distributions that people look at. If nothing else, there's the stuff in Turner and Sahani, but also automatic differentiation uses just Gaussian approximations. There are other options as well. And then you put a correction at the end. And so this comes from perturbation ideas from statistical physics, but what really matters is what we get out in the end, and it's the following. So V is the sort of bad, underestimating uncertainty matrix, covariance matrix that you get out from running mean field variational Bayes. It's this, you know, block diagonal, you know, thing that we're seeing illustrated here. I is just the identity matrix, so you know, get that for free. And H is something we can compute from the model with automatic differentiation tools. And so it's very straightforward. It's something that can be automated. And then you just pre-multiply V by this matrix that you can totally compute. You might be worried about this matrix inverse, but in fact, because of the nature of the problem, typically this will be something that has a lot of block diagonal structure, and so it's not so bad to invert from a computational perspective, and you get out a better uncertainty matrix, a better covariance matrix at the end, and in fact, in this case, it's perfect. And so, you know, if we look, for instance, you know, not just at a synthetic example, if we look at a real life data example, and you can do the same thing with the Criteo data or any of the other data we've seen, you can see that while mean field variational Bayes systematically underestimates these uncertainties, LRVB gets some closer to the exact values. So again, this line is the sort of x equals y line. It's where VB, or LRVB in this case, agrees with Markov-Chain Monte Carlo. So this is totally exact for Gaussians because Gaussians get the posterior means exactly. It does need a good posterior mean approximation though in practice. And so to the extent that we have seen on a number of examples that Mean field variational Bayes in particular, but BV more generally, seems to give good posterior mean approximations. This is a great way to get a better uncertainty. Now, the open question at this point is, okay, well, but we have seen some cases where maybe we're not totally sure the posterior mean approximation is great. And so what do we do there? And so there are other options there. I'll just mention, again, some interesting directions. So one idea instead is to say, you know, one of the big problems in all of this is that we have sort of too much data, which, you know, it somehow seems wrong, right? Like data should be a resource. It should be this great thing that we have. I think there's a whole Michael Jordan talk on data being a resource. And so we feel like we shouldn't have such a thing as too much data. Is there some way that we could extract the important parts of the data, but then not have so much that it becomes prohibitive to run our algorithms on it? And so the thing that we just talked about, this linear response variational Bayes, is like this post-processing step. What if instead we had a pre-processing step that just extracted somehow the core of our data, the really important parts of our data? And so the key observation here is that we don't need data to be boring and tall, just, you know, tons of data with very low dimension for there to be redundancies. Like imagine that I'm working on some sort of computer security application. I have a bunch of packets on my network, and, you know, some of them are email and SSH, and some of them are people maliciously trying to break into my network and do things that I don't want. And so maybe some of these packets are benign, they're totally good, you know, they're again this regular network traffic, and some of them are malicious. And I really want to identify probably which ones are which. And so from that perspective, you know, I might say, hey, there's so much network traffic, and it's usually high dimensional. There's so much information about every one of these packets that this could be a very challenging problem in practice. But then if I look at all of this traffic, I might find that actually there's just a few representative types of each. You know, maybe there's just a few types of benign traffic, again, like email or SSH, or, you know, looking at some web page. And maybe there's a few types of malicious traffic as well. And I think that if I ran, you know, if I substituted these representative types of traffic and just gave them big weights, and if I ran my algorithm on that, surely that would be very, very fast. You know, it doesn't matter if I use variational Bayes or MCMC. If I have 2 or 10 data points, like they're all going to be very fast. And so my sort of concern here is, well, yeah, it's going to be fast, but is it going to be any good? And so there's this really interesting idea from the computational geometry and sort of theoretical computer science literature called a Coreset. So it gets at the core of the data set. The idea is specifically to pre-process the data to get a smaller weighted data set. And I think what's really exciting about this literature is that they're able to get theoretical guarantees on quality. To say, if you make this data set in such a way, and then you run your algorithm afterwards, then you're able to guarantee that it's sort of epsilon close to the answer that you would have gotten if you had just run on the full data set. And so the open question at this point is, you know, can we develop Coresets for Bayesian inference? And why is that a challenging question? Well, if you look at the existing work from, again, sort of this theoretical computer science and computational geometry literature, it focuses on things like minimum bounding box problems and k-means clustering, and we just have so many more questions in Bayesian inference. Again, you know, we really want something like these probabilistic programming languages like Stan and the many other ones that exist, where you just say, here's your model, and then we can find the approximate posterior. And so that involves a huge amount of diverse tasks and geometries. So in particular, you know, you could have something where you have classification, you have regression, you have all the different types of each of those. You have hierarchical classification or regression. You have maybe some form of unsupervised learning, not just supervised learning, or semi-supervised learning. And there's plenty of forms of unsupervised learning that aren't just k-means and aren't just clustering. And so we want to be able to deal with all of those. And so we've done some work exactly on this problem, expanding Coresets for Bayesian inference. I'll just mention there's been some previous work on this, which is cool, but does not have theoretical guarantees. So there's this idea of data squashing, which is applying this sort of idea to logistic regression. If you're at all familiar with the Gaussian processes literature, you know that people use inducing point methods there, which has a similar flavor. But these typically don't come, or at least haven't come in the past, with theoretical guarantees on quality in terms of bounding the distance to the exact posterior mean or posterior variance. Also, I'll just mention, you might think, hey, can't I just subsample my data to be smaller? And there's a lot of issues that arise with that, actually. And I'll just go with the most unsubtle one for the moment. But I'll encourage you to check this out to see some more subtle ones. You know, suppose I subsample this data and oops, I lost all of the malicious data. And of course, that's the most important data for this problem. I would not want to just uniformly subsample that away. And it turns out this can happen in much more, subtle ways than this. If you actually have a two-class classification problem, you wouldn't subsample away one of your classes, but there could be groups within one of your classes that don't have special labels, and you could lose a very important group, and you wouldn't want to do that. And so what's nice about our work on Coresets for Bayesian inference is that you get a way to encode this so that you don't subsample away that important data. Okay, given the strictures on time, I'll not go into those subtleties, and I'll just hop ahead to diagnostics. Okay, so far we've talked about ways to correct things so that you actually get some kind of theoretical guarantee. Being able to say, oh, I can do this post-hoc correction, or I can do this pre-processing step, but somehow I want to get a guarantee that my posterior mean estimate is going to be close to my posterior mean, my posterior variance estimate is going to be close to my posterior variance. An alternative is to just run your algorithm and then check it. So sort of a post-hoc check rather than an a priori theoretical guarantee. And I'll first mention that ELBO or KL alone is not enough for this. So ELBO isn't enough because there's no scale. It sort of doesn't mean anything. You get a number, and it's good to like just check your algorithm to make sure that you are on track, that you don't have any bugs in your code, but that number you get at the end isn't really meaningful. Now, we have seen that KL, which you might be able to estimate somehow, is going to, we want it to go to 0. In reality, it won't quite go to 0, and then we have to ask ourselves, well, what do we get out of the number that we've actually approached? And I think that's the real challenge with KL, is that we don't know that typically our small enough numbers are small enough. Now, it may be that you get even smaller. You can say something, I think that's, may well be true, but a lot of the numbers that we encounter in practice are not small enough. So instead, in some recent research, in research that's about to appear at AI Stats, we provide some easy to compute bounds on Wasserstein distance. So you can still use your favorite KL algorithms, KL-based algorithms, but turn some of the, you can get the bounds that you care about. This is actually part of a whole validated workflow for variational Bayes. So this tells you sort of, what can you do differently instead of just running your optimization algorithm for minimizing the KL? What are ways that you can be more likely to get good posterior means and variances? And it's built on some really excellent work by Ajiboso Dieng and Yao et al. In 2018 as well. Both, really, really fun papers. And I think what we're just trying to do here is to have some theoretical guarantees to supplement these cool algorithms. Also, there's a lot of other work on diagnostics. There's another big area which has been, can we do things that are faster within MCMC, but don't have guarantees to speed them up? And so then can you do some post-hoc, check on that? And there's been some really cool work in that area as well. And so I just wanted to mention that. Okay, so we've talked about what is Bayes, what is approximate Bayes, what are we trying to do? And we've gone into a pretty deep dive on variational Bayes and mean field variational Bayes. Like any method in machine learning, they have pros and cons, and for every method that you use, you should be aware of the pros and cons. And so hopefully you're a bit more aware of those for variational Bayes and mean field variational Bayes here. But I want to emphasize that just because this method has cons doesn't mean that other methods don't. They all do, and it's just good to be aware of what they are, not only for applications where you really do care about this, but also in terms of, in your own research work, being able to, maybe make better versions of these algorithms that get away from some of those cons. So we've seen some of the benefits of variational Bayes that can work really well at point estimates. And we've seen some of the minuses that, without correction, there are these issues with uncertainty, although those can be overcome, but also some issues with point estimates. And I think there's some open work there still. And we saw some issues of where can we go from here. So I want to come back to the slide about all of these super cool applications. Again, the hope is that we're providing this tool that practitioners can really use, and we want them to make really accurate decisions and discoveries about coronavirus, about how are we saving people, how are we bringing people in ambulances, how are we helping people out of poverty, but also fundamental science like these black holes, understanding our universe, understanding exoplanets, and so on. And so I think there's a lot of area here, a lot of space to have a real impact, and it's important that we do this in a way that everybody understands what are these pros and cons, and understands how much they can trust the science they're getting out of them. And so I just want to end, this slide was in the slides that were passed around before, but I haven't talked through it yet. So I just want to end on this and point out, you know, if you're looking to read more about this and to get a better understanding, I think that's fantastic. I really encourage you to go through some of these exercises from our slides here if you haven't. There's some fantastic textbooks and reviews on variational Bayes. You know, even though Chris Bishop's is in some sense one of the oldest on this list now, I still think it's possibly one of the best. It really goes into just a lot of detail. It really goes into pros and cons and has this nice nuanced description. Obviously, nothing's going to touch on every issue, but I think that this one really does touch on a lot and gives you some good foundations. The experiments, many of the experiments that I talked about in this talk come from a few of our papers. So we have a NeurIPS 2015 paper as well as a JMLR 2018 paper that go into both some of the issues with variational Bayes, but as well as some of the solutions. So things like this linear response idea for correcting uncertainties. If you're interested in this idea of a validated workflow for variational Bayes and these bounds that actually get you something about, you know, understanding how close you are to posterior means, posterior variances, I encourage you to check out our AI Stats 2020 paper. I think AI Stats is like next week. It's right around the corner, so this is really fresh. We have this work on Coresets for Bayesian inference. A couple of papers in this direction are our JMLR 2019 paper and ICML 2018. The funny thing is the JMLR paper came first, but journals take a little longer to publish than conferences, so the dates look a little bit out of order, but that would be the order I would suggest checking them out. Start with the JMLR paper and then read the ICML paper.